Well, hello and welcome YouTube. Mr. Robbins back here with yet another brand new exciting video, all math basic course, and as always, it is an honor and a privilege to be serving you today, as it is every day here in my virtual classroom. Step on inside. Before we begin, a personal aside. I tried to record this video an hour or two ago, and I literally couldn't. For those who know me, this will come as no surprise. For those who don't know me, I'm a big eater, like massive eater. I eat a lot of food. Like whenever I have a meal, I sit down and eat a lot. And I had a cheesesteak from this place where I did this double meat option and all this kind of stuff. And when the guy made it, he said, this might be the biggest sandwich I ever made. It was an 18-inch cheesesteak with this double meat, double cheese, lettuce, tomato, pickle option, all this stuff. And he said, hold on, I'm going to weigh this beforehand. And he put it on the scale. He said it was 2.75 pounds. And I ate it. And fries and all that. And when I tried to record, I got about 5 minutes in before I said, I can't do this. So I'm trying this again. A couple hours later, round 2. I should be good. Anyway, let's get into it. We're in section 4.3 in the Big Ideas Math Integrated Math 3 textbook on graphing radical functions. Now, the radical to use can be like that square root. So a square root's kind of like an x squared, but opposite of or inverse of. We saw parabolas before. Now we're going to see something more of the sideways variety, but not fully so, and you'll see why. And you'll also see cube root functions. And we're going to see some other ones. I don't know specifically what types as a whole. I haven't gotten through the whole lecture, as I already mentioned. But let's go ahead and get started and see what this looks like. I'm going to attach graph paper down below in the description section, as well as a PDF of this problem set. You can find the actual problem set and the timestamps and which problems you're looking for. Without further ado, let's go ahead and give this one a second shot, shall we? Okay, we're going to graph radical functions. We are going to write transformations of radical functions. We're thinking a, h, and k, that kind of stuff. So we've seen that before, nothing new, once we understand the functions that we're talking about. And then we're going to graph parabolas and circles. And this is where it's going to get kind of interesting after what we learned beforehand, because, parabolas, we're not going to do the upward-facing parabolas. We will do sideways-facing parabolas. But to start with, they won't look like sideways-facing full parabolas. I'm already feeling something come up. I'm terrible with my body. Okay, or at least my my health, I should say. Okay. A radical function contains a radical expression with the independent variable in the radicand. We're talking about the x inside of the square root or something like that. When a radical is a square root, the function is called a square root function. What's a cube root? It's called a cube root function. Now, there are two different functions you're going to be looking at. Here's the square root one. Here's the cube root one as a general parent function. The book's going to be using a table. As you know with me, I'm going to go pretty tableless, and I'm going to talk about how I do it as well. Here's the parent function at y equals x squared. When you plug in 0, the square root of 0 is 0. When you plug in 1, the square root of 1 is 1. But when you plug in 2, you get the square root of 2, which is not a whole number. Square root of 3 is not a whole number. The square root of 4 is 2. And, if we substitute in numbers that will give us integers back out, those are my favorite kinds to get, which are taking the square root of a perfect square. Take the square root of 1, 4, 9, 16, if we could fit it on a graph, something like that. Take the square root of those values, plot whole numbers. That's going to be my big thing. So if you remember on parabolas, we go 1, 1, 2, 4, 3, 9 in both directions because you can square both directions. Remember, you cannot take square roots of negatives, so that's part of our domain. We're going to talk about that a little bit more. You can't take square roots of negatives, but we can take square roots of positives. So 1, 1, 4, 2, 9, 3. We're flip-flopping the x and y that we normally would have in those other ones. And that's how I'm going to go tablelessly outside of vertical and horizontal stretches. We'll get more to those. Cube roots. Now, we didn't graph many cubics, at least not parent function cubics, but here's this one. Cube root. Cube root of 0 is 0. Cube root of 1 is 1. Cube root of 2, 3, 4, 5, 6, and 7 are not integers, but the cube root of 8 is 2. The cube root of 8 is 2. So we can go 1, 1, and 8, 2, and plot points there as long as we can fit them. Now, you can take cube roots of negatives. The cube root of negative 1 is negative 1, and the cube root of negative 8 is negative 2, so I can fit those ones. I'm looking to do that kind of thing with my graph as I can fit them, and I'd love to do them in a non-table manner, honestly. In a non-table manner, apply the shifts and stretches and stuff like that within those parent functions. So hopefully we can recognize what I want to do with those, and that's the idea. Keep in mind, one more time, as I mentioned, the domain of this is not all real numbers. It's just x's that are greater than or equal to 0. You can only take square roots of positive numbers. So it's not a whole parabola because the square root of a positive number is a positive number. You can take not the square root of a negative number, but the opposite of the square root of a positive number is a negative number. So you're only going to get half a parabola at a time, either an upwards facing half parabola or a downwards facing half parabola that's opening to the left or right. Whereas this one is going to have an all real number domain and an all real number range going like, this way or that way or whatever else like that with the graphs. Anyway, let's mosey on forward and take a look at a couple of their examples they have. Graph each function, identify domain and range. Now, the first one, they go straight into what would ideally be a horizontal stretch, this 1/4. If you recall, they're not talking about it yet, but I'm bringing it up now because they're going straight into table. Now, they're plugging in values that are 4 times larger than they normally would. Why would they do that? Because they're going to be divided by 4 in a second. This is why this is a horizontal stretch. This is why the x's have to be 4 times as big to just get a y value out that's, the same as it would have been if this 1/4 wasn't there. That's why it's a horizontal stretch when this is a 1/4. That being said, I could take my idea of the graph and horizontally stretch it by a factor of 4. Instead of 1, 1, 4, 2, 9, 3, I'll go 4, 1, 16, 2, 36, 3, if I could fit that. And you do have those. You have over 4 up 1 and over 16 up 2. They plotted some points in between that I personally wouldn't care to plot. However, this is the square root of 2. This is the square root of 3. And they move on forward. And there's the graph. It's still centered at the origin. And I don't know if they call this a vertex anymore. I don't believe it is. If I say the word vertex, hopefully you know what I mean. It's that leftmost half that would have been the same thing on the other side. It's not a true vertex, but there it is. The second one was y equals -3 times the cube root of x. Now, when we consider this, once again, they're using a table. They take their y values and they're multiplying by -3. But what happened to this graph? Think about our transformations. And again, the next page we'll talk about them. But it got flipped over. That's what the negative was. Remember, last time the graph went this way. Now it's going this way. And it got vertically stretched. It's 3 times taller than it was before. So instead of now going 1, 1, 8, 2, it's now going 1, 3, 8, 6. Did they fit 8, 6? Not quite. It's out of range from their thing. But that's what we would do. We would triple our heights. So I'm going to get into those as they talk about transformations because they're going to do more than just horizontal and vertical stretches and flips. But I wanted to just mention why the graphs changed from what they were before. Now, we'll talk about domain and range for these. I'm sure they're going to ask about them, so get ready for us to make changes to these as h changes or as it flips over. H and k, I should say. All right, here are some transformations. They're just mentioning them. Notice that f was a horizontal stretch, g is a vertical stretch, and a reflection in the x-axis. How come? Well, we're going to talk about hk, x minus h, or f of x plus k is your horizontal shift and your vertical shift. No changes from before. I'm not going to state much about them, but they will exist inside the function for horizontal. They will exist outside the function for vertical. Okay? And opposite of when it's inside. -2 is 2 to the right, things like that. A reflection, you can flip it over in the x direction, or, in the y-axis, I should say, but flip it over left to right versus flip it over up, down, right here. Flip something over up, down. Excuse me. I always go to vertical stretches first. Make something 4 times taller. Vertically compressed by a factor of 1/5. Keep in mind that the other thing's changing, though. Y is changing, but instead of going 1, 1, 2, 4 and changing the 4 to something, whatever, now it's 1, 1, 4, 2 and changing the 2 into something. So it'll look a little different. And horizontal stretches. Remember, this is a compression. This is a stretch. We can turn some horizontal stretches into vertical compression, whatever, vice versa. If we take its square root, it depends on the number. If it's a perfect square value, you might see me do it. All right, let's see some of those examples. Let's look at the square root of x as f of x, and let's transform it to this g of x as x minus square root of x minus 3, and then plus 4. So now our h is 3 and k is 4. That means take your original graph you would have done centered at the origin here, and we'll go 3 right and 4 up. And then do the graph as you normally would from here. 1, 1, 4, 2, etc. That'll be the appearance of that graph. Keep moving forward. Domain is now different. X has to be greater than or equal to 3. Range, y is greater than or equal to 4. And you can see that that's where your x and y values start on that graph. I don't know where they mentioned it. They did not mention domain and range on that one. So I'm saying that one out loud. This one is g of x, or from x cube root of x, we have -8, the cube root of -8x. Now there's something I can say about this one. They're actually bringing it up over here, so I'll leave it for a moment. But on this one right here, it's a horizontal reflection. So instead of, going this way, it's flipping over to that way, right? So instead of going in black, it's now blue. And it's horizontally compressed. It's 8 times smaller than it would have been. So instead of 1, 1, it's going over 1/8 up 1. Instead of going Over 8 up 2, it goes over 1 up 2 because 1 is an eighth of 1. Now it's going 1 to the left to go up 2, and it's going right 1 to go down 2. That being said, if they took the cube root of the negative 8, it would turn into negative 2 times the cube root of x. And that's what they have written. Sorry, I'm using my mouse for this. That's what they have written over here. You can turn a horizontal compression into a vertical stretch. I guess it's technically a stretch in that case because it's just so massive. So it's 2 times larger. So instead of 1, 1, 8, 2, it's now 1, 2, 8, 4. Because it's vertically stretched now in that case. All right, let's look at some modeling with mathematics. They have a function with a square root. It approximates the number of seconds it takes a dropped object to fall on Earth. I guess it's kind of flipping some things around. Now time is your y value, whereas distance is your x value. There's a flip-flop there. This function approximates the number of seconds it takes on Mars. Write a rule for m. How long does it take a dropped object to fall 64 feet on Mars? Write a rule for m, isn't it right there? I don't know. We'll see what they're talking about. Oh, they're doing it based on Earth. I missed that. This is Earth. That's not a variable right there. So you do 1.6 times. I didn't get nearly this far last time. I gave up after 5 minutes. Probably even less. Anyway, you're writing a function that's simplified right here. So here's a function for Mars, and you can plug in a distance here to find out how long it takes on Earth. So after to drop 64 feet, it's going to take 3.2 seconds. It's a substitution oven. There's not much I have to say about it. We're not doing anything specific. We're not even graphing there. They're not talking about domain and range, so we'll leave it. Writing a transformed radical function. We'll see what they have to do with this. Oh, this is where they're describing something to you when you're using it. So this is literally no change. We have a horizontal shrink by a factor of 1/6. Remember, the 6 goes inside of here. We do a 6 times instead of 1/6 times inside your function. So there's no real change to these problems than previously. I'm not going to dive deep into these. If you do after that a translation 3 units to the left, remember that's an x plus 3 on the inside of the function. However, it's just substituting in for x. So it's still 6 times x plus 3, and they're distributing that out. Even though this doesn't look like a great graphable form to me, it's not a great graphable form. I actually prefer this form, if anything. This is just a simplified version of what they have. Now, there's nothing to take the cube root of in this instance. Don't try and expand it or contract it or anything. We'll leave it like that. And graphing parabolas and circles. Now, you might have graphed circles in, I guess, IM2. And of course, we've graphed parabolas before, but these are sideways parabolas, and you'll see what they have to do with to be a sideways parabola. It says use a graphing calculator to graph 1/2 y squared equals x. Now they're doing the graphing calculator. I can go without it. It depends. I guess it depends on the appearance of the problem. But in this case, they want you to solve for y. Your graphing calculator only knows y equals, at least the TI-83 does. So you got to get y by itself. We have to multiply both sides by 2 and take the square root of both sides. But if you recall, as a function goes, this should be plus or minus the square root of 2x. That means there are 2 different equations. There are 2 different equations. To make a full parabola, this is not a function. It fails the vertical line test. This is a sideways parabola. So in order to make it a function, it's not one, but you have to make 2 separate functions to complete the graph. y1 equals positive square root of 2x, and y sub 2 equals negative square root of 2x. You make 2 different equations. Your graph will literally draw one of them, and then it will draw the second one. And it says, here's your equation, sir. And then it completes it. So I guess if they say use the graphing calculator, we'll use the graphing calculator. If I think I have a way that I can do it, a graphable one that I prefer to do myself, I'll do that as well. If you want to use a graphing calculator to graph a circle, you know what? Part of it is, even if it's not about graphing ourselves, because maybe we've done this in IM2, and you might know this is centered at the origin and has a radius of 4. But if they're teaching you how to graph using a calculator, you'd have to get y by itself. You'd have to subtract x squared from both sides. And it's one of the only times that I'd actually recommend you don't write in standard form, that you actually subtract the x squared on this side. This is the form that you would generally see. Take the square root of both sides, and now you have plus or minus the square root of 16 minus x squared. Do not take the square root of 16 minus x squared and turn it to 4 minus x. That is not what that is. You should know that of all people, right? In fact, it's a difference of 2 squares that is 4 minus x times 4 plus x, but it's still inside the square root. So no, it doesn't just become that. It's not the same thing multiplied twice. So please, please, please don't try and take its square root. That's just the appearance. But there are 2 different functions. Positive square root of 16 minus x squared, which is this here. And then negative square root of 16 minus x squared, which is this here. Together they complete that circle. Again, like I said, center 0, 0, radius is 4. Maybe that's something you remember before. Here are your x-intercepts, here are your y-intercepts. Once again, circles are not a function, so you have to make two different equations out of it. So if they say use a graphing calculator, okay, we'll use the graphing calculator, that's fine. Okay, that thus ends the lecture. Let's get into problems 1 and 2 in the vocabulary and core concept check. Let's complete the sentence. Square root functions and cube root functions are examples of radical functions. Radical functions. When graphing y equals a times the cube root of x minus h plus k, translate the graph of y equals a times cube root of x, h units, well, in terms of minus, I guess h units to the right, and k units if it's a plus k, k units upward. Now, if h is truly a negative number, it'll say x plus 1 or something, and we'll go to the left. And if it's at minus 7, then we'll go 7 units down. But they're just talking about, maybe I should say horizontally and vertically, but maybe they're talking direction as well. I'm not actually sure which. And with that said, let's now jump into the actual problem set. We are going to problem, let's find out together, actually 60 something. We're going to problem number 68 here. A lot of graphs, graph paper will be attached. I'm already indecisive as to whether I'm going to be using this graph paper or this graph paper. Now, if I do use this graph paper here, guys, I would recommend you'd rotate it this way to complete more of the graph that you can. And I'm thinking about using this one instead. Depends on the plots we can point. I say that often, the points we can plot. It depends on the points we can plot. But I want to get farther out that way, the same way we'd go tall with quadratics too. So I might be looking to use those ones. Okay, numbers 3 through 6, we might have to begin that way though. Match the function with its graph. So on number 3, we have automatic transformations here. F of x, let's use black. F of x equals square root of x plus 3. Now in this case, as far as if I write vertex, I mean that part that's like a vertex in this case. Vertex would be negative 3, 0. There's no change or flip over. In fact, none of these have flip over. The only change is translation. We're going 3 units left, no units up or down. So it's not A. Excuse me, it's not A. It looks like it's B. It's going 3 units left and whatever. So I'm just going to go ahead and mark that as B. I'm not doing too much on these problems, just giving you a heads up on how these transformations appear, as there's really no difference from what we had before. So B is now out as one of our options. I'm guaranteeing myself that it's B. Number 4, we have h of x equals absolute value, square root of x plus 3. And this time the plus 3 is on the outside of the function. That means it's more of a k value. So this vertex, okay, vertex is this guy. Remember what I was talking about here? Reference point, center, whatever you want to call it. Vertex, quote unquote. Vertex is 0, 3 this time. We translate 3 units up from the origin. So A is 3 units down from the origin. This is also horizontal translation. Looks like it's D. 3 units up right there. So I'm going to mark number 4 as D. Number 5, f of x equals square root of x minus 3. I think I'm going to be able to get through this. I think I'm okay. If you missed my very beginning intro, I inhaled too much food. This one is going to be at 3, 0, and I had trouble recording the first time. That's 3 to the right. So 3 to the right looks like F. Oh, why is A? Oh, these are crossed out. Okay. B, D, F. So we went down the right side there. Number 6, there's an x, square root of x minus 3, but this time the minus 3 is outside the function. That's going to be 3 units down. So this vertex is at 0, -3. So the last one that's on an axis looks like it's A, 3 units down from there. These two are off the axis. We'll have to make sure we know which one is which. Number 7. Quick whiz bang on questions here. I keep saying absolute value. H of x equals square root of x plus 3 minus 3. That vertex is at -3, -3. So 3 left, 3 down. And that is E, option E. So it looks like option C is next. And without even knowing what the question is on C, let's look at the graph. It goes 3 right and 3 up. So this must be square root of x minus 3 here and then plus 3 outside. The only thing is I don't know what function it is. I'm going to make a guess. H of x. It's f of x. Wait, h of x was the last one. F of x equals. Should just default to f of x. F of x equals, and then this must be C. This is at 3, 3, 3 right, 3 up. And that's the matching equation at least, and that's C. Okay, I'm going to sip of water first. I am dehydrated. Okay, numbers 9 through 18 will graph the function. Identify the domain and range of the function. Looking at the problems, I'm going to begin with the scaled graph, the actual numbers themselves right here, if you don't mind, just so you can see the numbers on them as I do them. After that, if they do more stretches of sorts, because a lot of them look like compressions, honestly, which is probably a good thing for us. But if we get into more stretches, I might jump into more of the other, this kind right here instead, okay? But for now, we'll go ahead and stick with these ones. I hope that's all right. Identify domain and range, however. So number 9, we do have h of x equals square root of x plus 4. Now, there's no shame in identifying domain and range after we draw the graph, and in which case, definitely range. Domain you might want to talk about before the graphs, but let's just start with this graph as we think we know how this thing goes. First of all, the square root of x is an up and to the right kind of graph. It's only a half-facing parabola. But the plus 4 is a translation 4 units up. So from this graph that's normally centered at the origin, instead we're going to go up 1, 2, 3, 4, and our vertex guy is right here. In my tableless graphing format, if I go over 1, I go up the square root of 1. If I go over 2, I go up the square root of 2, and maybe I don't know that number. Square root of 3, I don't know that number, but the square root of 4 is 2. So over 1 up 1, over 4 up 2, and the next perfect square is 9, over 9 up 3. All right, we can do those. And we can plot the rest of the points of that graph just like that, simply. So just translations only with respect to that. The domain of this guy is not all real numbers. It's x is greater than or equal to 0. As it makes sense, you can only plug in numbers. You can take the square root of 0 or larger, but that's it. The range is affected by the plus 4 here. The y values are 4 or larger. Only 4 or higher are the graphs, the points that appear on the graph. Okay, number 10. We have another square root, and it looks like just a vertical translation once more. G of x equals square root of x minus 5. This is a vertical translation 5 units down of the same parent function, no other change to it. So this one, we're going to start down here as we now go over 1 up square root of 1, over 4 up square root of 4, which is 2, over 9 up 3 like that. And that can be our graph as we complete it. Same thing. Now, domain is still x is greater than or equal to 0. No change there. That's only really going to change when things affected inside your function change. Range did get changed, though. Y is greater than or equal to negative 5 in that problem. Okay, numbers 11 and 12 are cube root graphs this time. So number 11 has a couple changes applied to them. We have g of x equals negative cube root of 2x. Now, the changes here that I want to actually make mention of this time are we are reflecting across the x-axis, and there is a horizontal compression factor of 1/2. Okay, everything is half the size that it was before. So the original cube root function, let me remind you what the original cube root function looks like. Centered at the origin, and this time we'll call it more so center, we'd go over 1 up 1, and the next perfect cube is 8. So over 8 is where you'd go up 2, and you can get negatives as well. Now, this is not the answer to this question, guys. This is just the parent function, what would be like an f of x compared to this g of x right here. So this would be the original. Now, what we're going to do with this is the following, right? We are going to reflect it over the x-axis, so it's going to flip over this way, like that. I guess the points didn't go with it, sorry. But we're going to reflect over the x-axis that way. And then we're also going to horizontally compress this thing, like whatever, right? It's going to shrink like that twice as much. So let's get the graph that we're trying to do here. We're going to stay centered at the origin, and this time we actually do call it a center because there's no real vertex for this one as a for sure. It will flip over, so instead of going right and up, we'll go right and down. But it's going to be horizontally compressed. Instead of going over 1 to go down 1, we'll go over 1/2 to go down 1. Instead of going over 8 to go down 2, we'll go over half of 8, which is 4 to go down 2. The next perfect cube is 27. So if you were going to try and fit one, instead of going over 27 to go down 3, we can go half of 27, which is 13.5. That won't really fit, but 11, 12, 13 would go down 3 like that. Sorry, 13.5 even. You go over 13.5 to go down 3. So that doesn't really fit. But cube root functions do go the other direction as well. We'll go left 1/2 to go up 1. We'll go left 4 to go up 2, like that, and left 13.5 to go up 3 if you truly wanted to get an appearance of that portion. I'm not really going to fit that part. I just wanted to give you the idea of it as we could finally get up there. But this cube root function is going to look like this. Now I get to go faster in future problems. You actually saw the most complex part of the cube root function right then in terms of the first time we saw one. Domain and range are all real numbers. That will be true for every cubic function that's not based off of some sort of algebraic model. Okay. Number 12. To answer one part, domain and range are all real numbers on the cube root function. So that's the first part we can talk about. Number 12 is f of x equals cube root of negative 5x. Now, having negative on the inside or outside doesn't really matter. Cube root of a negative number is a negative number. So if you want it on the outside, go ahead and do that. I'll leave the 5 on the inside the same way we did before. You can either say reflect over x-axis or reflect over y. It's the same graph. All right, a cube root function that, remember the cube root function that I just drew last time, the parent function, where I was doing like this and I said flipped it over? There, I have a feature on my thing where I can either hit reflip up down, which is this, okay, remember that, or flip left right, which is this. Now, the only slight difference is because I drew it so stupidly that you actually might see the difference between that little bumpy curve there and then this little part that curves up if I go up, down, right there. Of course, right, there's a difference there. But it's no change in the actual graph because flip over that way is going to stay the same no matter what. So whichever one you do is up to you. However, there's a horizontal compression by a factor of 5 this time. So we divide our x values by 5 to go up just 1. Now, we are going to go right and down and left and up. So instead of 1, 1, 8, 2, 27, 3, we divide our x's by 5. We go over 1/5 to go down 1. What is 1/5 of 8? 8 fifths, 1 3/5. So you go over 1 3/5 to go down 2. It's 1.6. We can fit actually a few points on here, guys. What's 27 divided by 5? That's 5.4? 5.2? Hold on. 5.4. You go over 5.4 to go down 3. 4 cubed is 64. What's 64 divided by 5? That's 12 4/5. So 10, 11, 12 4/5. We can go down 4, right? You go over perfect cubes to go down that cube root amount. So that kind of fits. Oh, here's 0, 0, by the way. And 1/5 up 5, 1/5 up 1 over 2 and, what was it? 1 3/5 to go up 2. Over 5.4, 5 2/5 to go up 3. And 12 4/5, 11, 12 4/5 to go up 4. I want to actually try and fit those ones truly. And there's your cube root function for this one. Now, if you'd like to plug in a table, guys, nobody's stopping you. The solution guide video is built for efficiency in the future. I'm speaking on some things a little slowly to begin with. Of course, I'm going to speed it up as we go along. Domain is all real numbers. Range is all real numbers. Okay, number 13 actually this time has a slight change in what we're doing because this is now a vertical compression. So on number 13, we have g of x equals 1/5 times the square root. We're back to square root of x minus 3. So the x minus 3 portion, this is one where I would probably, in normal circumstances, prefer to use the other kind of graph, the stretched out one. Again, I'll save that for problems probably beyond this portion. The x minus 3 means we got to shift this 3 units to the right to start. Now, instead of 1, 1, 4, 2, 9, 3, we got to divide our heights by 5. So instead of over 1 up 1, we go over 1 up a fifth of 1, which is 1/5. Instead of over 4 to go up 2, we're going to go up now just 2/5. Instead of over 9 up 3, 10, 11, 12, we're going to go up 3/5 like that. So it's going to kind of just look linear to you because of just how small it is. Again, it doesn't have so much character in this direction. It's very small, but it just goes upward like that. Your domain is x is greater than or equal to 3 this time. Think about it. If I substitute 3 in here, 3 minus 3 is 0. That's the smallest number I can plug in. If I plug in 2, 2 minus 3 is -1. I can't take the square root of -1. That's too small of an x value to plug in here. So that makes sense for our domain, and that makes sense why we're 3 units to the right. Range is y is greater than or equal to 0. We're still above, on the y-axis, on the x-axis or above. Number 14, also a vertical compression. Here we go. So number 14 is f of x equals 1/2 times the cube, oh, this is a cube root though, of x plus 6. Man, I'm really thinking of getting the long graphs here. Really pushing, really testing me. Should really get in the long graphs. 1/2 times the cube root of x plus 6. Now x plus 6 means 6 to the left for our center right here. The 1/2 is a vertical compression. This time cube root is going to be right up and left down. Instead of 1, 1, we're going to go over 1 up half of 1. Instead of over 8, boom, up 2, we're going to go over 8 up half of 2. And we'd have to go over 27 to fit the next number, which I probably almost could have fit on the on the longer graph. Over left 1 will go down half of 1. Over 8 we'd go down half of 2. That can't really fit, so I'm just going to kind of just get these ones in. So there's that guy. It's not truly flattening out, guys. It's still working upward. And then it curves down and out this way. Down and out this way. Like that. So cube root function is cube rooting. Domain, range, all real numbers. And we move along. Number 15. Number 15, we have f of x equals 6x to the 1/2 power plus 3. Now, coming off of the previous sections that we had, it's probably best that we write this as the square root of 6x and then plus 3. Now, this 6 inside of the function refers to a horizontal compression. We have a horizontal compression factor of 1/6. Okay, we are going to translate this 3 units up in the meanwhile. So, horizontal compression factor of 1/6 means we have to divide our x's by 6 compared to how much we normally would have gone over to go up the same height. Now, we start up 3 units like this for our vertex. Remember, this is a square root function. Instead of 1, 1, it's over 1/6 up 1. Instead of over 4 up 2, we're going to take 4 divided by 6, which is 2/3. We'll go over 2/3 to go up 2. This is not linear, by the way. I got to figure out my way to show this best. We're going to be able to fit a lot of points, guys. 9 up 3. No, divide 9 by 6. That's 1.5. 1.5 up 3. There's the curve. 4 squared is 16. So 16 divided by 6 is 2 and 2/3. Excuse me. We go over 2 and 2/3 to go up 4. I'm going to plot as many as I can fit. 5 squared is 25. 25 divided by 6 is 4 and 1/6. So 1, 2, 3, 4 and 1/6 to go up 4. 36 divided by 6 is 6. Hey, over 6 to go up 6. And last one I can fit. 49 divided by 6 is 8 and 1/6. So that's 6, 7, 8. 8 and 1/6. We can now go up 7. Remember, you're going over a perfect square amount. We got to divide that over a perfect square amount by 6, and then we can go up another y value from before as we previously would have. And there is a very nice version of that graph. I'm fine with it. I like the tall graphs like that. Domain, x looks to be greater than or equal to 0. Range is y is greater than or equal to 3. Okay, number 16. G of x equals, whoops, -3 times x plus 1 to the 1/3 power. That's also equivalent to -3 times the cube root of x plus 1. This is a flip over, and it's a vertical stretch. We do translate 1 unit over, and I'm going to start with that. We'll go 1 unit to the left. We're going to flip this graph over, so we'll go this way instead. And we need to stretch it 3 times taller than before. Instead of 1, 1, it's 1, 3. Instead of over 8 to go up 2, we're going to go over 8 to go up 6. 2, 4, 6, like that. And we're going to go right. We're going to go right 1, down 3. And right 8 to go down 6. It's a very tall cubic function, comparatively. Nice. One shot. Domain range, all real numbers. Feel a little faster now? Yeah. Number 17, fourth roots. Hey, fifth roots. I don't dabble in these very often, but now let's think in terms of, you know what? I probably got to go with these kinds of graphs now. I'm going to use these ones now just because the numbers get so big as far as what we can plot. I don't even know if I can fit what I want to plot to begin with. We'll see. Let's hope we can do something with these. Now, number 14, again, you can use a table, or number 14. Number 17, you can use a table all you like to. H of x equals negative fourth root of x. Now, first of all, we never saw even negative square roots, so let's just talk square roots. Our square root graphs would normally go like this. So a negative square root would, of course, flip over. It would end up going like, instead of this way, I'm trying to flip it over. I missed clicking on the right feature. We would instead go this way, right? That would be a negative square root. Negative fourth root's going to do the same thing for the same reasons. You can't take square roots or fourth roots of negative numbers, so it only goes one direction in that way, and it's going to go downward. Now, how much downward? Not much compared to its x values. You got to go over, first of all, we're at the origin. Going over 1 will go down 1. The fourth root of 1 is still 1. But what's the next perfect fourth power number? The fourth root of what gets us 2? 16. And that's why I needed this graph here. I have to go over 16 to go down 2. That's the next one that I can plot on that one, guys. So that gets a little bit long there, and it only goes downward. It's just a downward facing graph. Oh my goodness. Oh my dear Lord. And then you got to go over, what's 3 to the fourth? 81. Guys, you got to go over 81 to go down 3. I mean, you can change the scale of your graph. That's fine. But you got to go over 81 to go down 3. I want to write domain and range. Let's just write it up here. Domain, x has to be greater than or equal to 0. Range, y is less than or equal to 0. In this case, your range, it goes downward from 0 to plot those points because of the reflection in the x-axis. And then number 18, I also probably need to use the long one. Now we're talking fifth roots. Thankfully, they're saving us a little bit with a horizontal compression. So let's use that same kind of graph here. So we're going to do, trying to lock it in place. I got a lot of keyboard commands I got to hit here, sorry. We have h of x equals the fifth root of 2x. So a fifth root function is like a cube root function in that it kind of goes both directions. Domain and range is all real numbers. It'll have kind of a squiggly like that, right? It's centered at the origin, but it is horizontally compressed by a factor of 2. Now, normally we'd go, the fifth root of 1 is 1, but we got to go half that amount on x, over 1/2 up 1. Now, the next perfect fifth power quintic thing is 32. 2 to the fifth is 32. So the fifth root of 32 is 2. Now, I can't fit 32 here, but we're dividing our x's by 2 anyway. So we divide 32 by 2 to get 16. We go over 16 to go up 2. So you're like, hey, that's like the fourth power one. Well, the difference is all the points that go up from there because we go over 1/2 to go up 1, not over 1 to go up 1, which means everything in between changes. But you won't care about it that much. The other difference is it's a fifth root function. So now we can go left and down, over 1/2 down 1 and over 16 to go down 2. So I had to go long with these ones in order to fit this properly, and we're going to go ahead and sketch that best as... Wow, that looks very, very flat. Let me try that from this side, actually. Let me first start from here and kind of shoot outward like that. It's real. This is really a tough one to plot. I suppose you can try some points in between. That's not my goal. I could do this better with pencil. It's just really hard to do on a computer. because I'm not actually touching the screen. I'm using a tablet to try and focus on what it is, so I'm not guiding myself from there. Hopefully you know what I mean. Anyway. Swinging the chain, swinging the chain. Now, 3 to the 5th power is 243. I know we divided by 2. We have to go over 121.5 just to go down and up another y value. I mean, that's pretty crazy. All right, there's the end of those ones. Domain is all real numbers. Range is all real numbers. Let's move forward to the next set. Let's describe the transformation of f represented by g, and then we'll graph each function. Now, I started to write a couple from the previous first ones. I guess we're doing the same stuff, but we probably have to write them out as sentences. So we're starting with it says graph each function. So we need the parent function as well as the transformation. I think I'm going to stick to the long versions of the graphs now, and I'm going to have some in play for my square roots and cube roots, and by the end we have another fourth root and fifth root. All right. So let's first talk about what we have. I'll probably type it a little bit smaller because we got to fit a little bit more in the long direction this time. The graph of G is a translation 1 unit left and 8 units up from F. Okay? They don't ask for domain and range for these, by the way. What I'm going to do first, obviously, is I'm going to graph that parent function. I will probably lock that in place afterward and have a copy and paste. Now, x, I have a little more wiggle room to do so, or the f of x. So here's my origin. Square root of 1 is 1. Square root of 4 is 2. Square root of 9 is 3. And square root of 16 is 4. So let's get a pretty looking one, because this is the one I'm going to use in the future for all of my other ones. In fact, I can probably copy and paste this whole set right here for my translation, but I'll leave it. I think we got to do vertical stretches and stuff later. All right, let me group this together as one graph. I'll go ahead and keep that one in. Okay, I'm going to keep this off to the side for future use. Okay, so my g of x is the same exact graph as f of x, only we go left 1 and up 8. Now this will barely fit here. 1, 1, 4, 2. That's kind of all I can fit. I'll do one more. 5, 6, 7, 8, 9. 1, 2, 3. Over 9 up 3. So it is the same graph, it's just translated over like that. If I did try to pretend like I could fit more, it'd be like that. But that's the graph, right? That's one compared to the other. Okay, number 20. Same parent function, square root. So let's go ahead and take that same one. F of x is the square root of x. And g of x is 2 times the square root of x minus 1. Okay. Let's first describe it. The graph of G. Graph. The graph of G is a vertical stretch by a factor of 2, followed by a translation 1 unit right of F. Okay. So for this one, we'll take that original parent function, which is this guy, right? Same one. And we are going to go, I'm going to start with the translation. I already know my vertical stretch is going to apply, but I'm going to start this thing right 1 with that vertex. So now we'll go, instead of 1, 1, 4, 2, we have to double our heights. So 1, 2, and 1, 2, 3, 4, comma, 4, and go over 9 to go up 6 instead of 3, right? We're doubling these. And go over 16 to go up 8. This is going to be my favorite graph as far as completeness, how much I can really cover both parts of the grid. So much character. Oh, yes. And there's one compared to the other on that. That's the new graph for g of x, okay? Number 21 and 22, we have cube root functions. So number 21, and I will have to graph my cube root function first, if that's okay. F of x equals the cube root of x, and g of x equals negative cube root of x minus 1. Let's describe first. We'll get to the graphing afterward. The graph of G is a reflection in the x-axis from F, followed by a translation 1 unit down. Now, what does F look like, the parent function? Well, we've seen a few of these. Let's see another one. Let's get it ready to go. The original f of x in this case will be, we start at the origin. Cube root of 1 is 1. The cube root of 8 is 2. That's not 8, that's 9. The cube root of 8 is 2. Cube root of 27 is 3, and I can't nearly fit that. The cube root of negative 1 is negative 1, and the cube root of negative 8 is negative 2, and I can't quite fit the cube root of negative 27. That being said, I still want to graph this thing outward. Just make sure you don't go down to negative 3 quite yet, because we don't actually hit negative 3 until x equals 27. So I'm going to still do what I can here. Probably won't be the prettiest. That is not the prettiest. I'm going to try. I failed that way before. I'm going to start going this way and see what I can do going out the other direction. I'm going to pretend like that's decent. Now let's try this direction here. It's all right. That's all right. Let's pretend like that's good. Okay. So there is our original cube root graph. It's kind of meh, but we're going to flip it over and we're going to shift 1 unit down. So flip over means this way, shift 1 unit down means that way, right? So I'm going to start at 0, -1, and now we'll go left 1 to go up 1, and left 8 to go up 2, like that. And then right 1 to go down 1, and right 8 to go down 2, like that. So I'm going to kind of wing these graphs a little bit more quickly now that we have the parent function there. So there's 1, and there is the other. Okay. All right, there's our g of x graph. All right, number 22. I'll keep that up there while you're maybe looking at it. You can, of course, pause the video. Number 22. We have f of x equals cube root of x. Once again, we'll take the same parent function graph we had before. And g of x equals cube root of x plus 4. Oi, 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 oi. And minus 5. Okay. So, the graph of g, just translations this time, right? The graph of g is a translation 4 units left and 5 units down from f. So those two things are going on, and let's go ahead and take a look. With this parent function, we'll take that same function that we have. We'll just go 4 left, 5 down. So 4 left, 1, 2, 3, 4, 5 down, 1, 2, 3, 4, 5. Boom is right here. Otherwise, it's 1, 1 over 8 up 2. It still can't fit 27 over to go up 3. So over 1 down 1 and over 8 down 2. Over 8 down 1, 2 right there. Okay, just a translation. Whoops. Still can't fit 27 over from -4. It's getting quite close, though. I gotta admit. It's getting quite close to being fittable. So you're getting quite close to getting up there. So I'm pretending like I'm getting closer and closer. Okay. And it should be smoother. It should be more of a curve, guys. I'm not really selling. I'm not really giving the selling point of that. A little more like that. All right, number 23. It's not really angled. I hope you know that. F of x equals x to the 1/2. We know that means the square root of x. Let me copy over that graph because I didn't from the previous page. So I need to get my original parent function for that one. I need this guy right here. So f of x equals x to the 1/2 power. G of x equals 1/4 times -x to the 1/2 power. Okay, first thing I'm going to do is change g of x. As we know, f of x is... Oh, that's the wrong graph. That didn't copy over. I'm sorry. Let me try that one more time. Copy. Okay, that's the right one. Okay. So first of all, we're taking a look at that one, right? It's really square root of x, and for our g of x, we're really looking at 1/4 times the square root of -x, like that. Now, you might say, well, you can't take the square root of a negative number. You're right. You can't take the square root of a negative number. So what do? We plug in x values that aren't positive. We can't plug in positive x values because, like, say you plug in 1, -1, you can't take the square root of -1. We can't plug in positive x values. We have to plug in negative x values and 0. If you don't understand that part, let's talk about domain instead. Remember, it's this thing the thing we're taking the square root of has to be greater than or equal to 0. So -x has to be greater than or equal to 0. Well, how do you solve for x in a scenario like this? -1 is multiplying by x, so you divide by -1. What does that become? X and 0, but you flip the inequality. This is your domain. Your x values have to be less than or equal to 0. What does that mean for your graph? Same thing as it always means for these negatives inside the function. It's a reflection in the y-axis. It's a horizontal reflection. It flips it over this way. From this kind of graph to this kind of graph. It's now going to go left and up instead of right and up. And by the way, there's a vertical compression. So those are the two things we have to describe. That's why it is the way that it is. Anyway, so with all of that in mind, let's go ahead and get that set up and ready to go. We have to describe it first, and then we'll graph it. So the graph of g is a vertical compression, or shrink, by a factor of 1/4, followed by a reflection in the y-axis from F. So for this one, the origin, the vertex is at the origin, all that, there's nothing changing there. But we are now going left to go up. And we're not going right at all. So we're going left. Left 1, we got to go up 1/4 instead of 1. We go left 4 just to go up 2/4, which is 1/2. We go up 9 to go up 3/4. And we go over 16 to go up 4/4, which is 1. Again, these will look kind of linear to you. In fact, this first point, it looks taller than my second point, which is not the point. It's still a curve. It's still a kind of parabola, half parabola looking thing that looks like that. Bitty small. All right, number 24. You thought that looked small. We still have vertical compression, but this time with the cube root. And I ran out of room, so let me copy and paste this one over. I have to do a lot of copying and pasting from things that I have on a sidebar. Like I take this thing and I move it over off to the side where you can't see it. I got more screen space than you're aware of. Number 24. We have f of x equals x to the 1/3, and g of x equals 1/3 times x to the 1/3 plus 6. Of course, this is also cube root of x, which you see pictured below. And g of x is also 1/3 times the cube root of x, and then the plus 6 on the outside. So what's our description stuff compared to our original parent function? What are we doing? We are vertically compressing by a factor of 1/3 and shifting it 6 units upward. All right, so there's the answer. Where's the graph? It's still going to go the same direction, but we got to start upward right here. Over 1, up 1, and take 1/3 of 1, which is 1/3. Over 8, up 2, and take 1/3 of 2, which is 2/3. And again, we can't fit that because we can't fit 27 over. So left 1, down 1/3. Left 8, down 2/3. Again, don't make it purely a straight line, but it's going to be a little more a little straighter looking than your previous ones here. Really still trying to accentuate this curve a little bit as it kind of goes into there. Remember, this thing would curve the same way like a U-shaped parabola does, with the exception of it goes into negative realm instead of curving back the other direction. So it really should have more of a curve than even I'm bringing on with it. So I'm trying. It's really hard with these features here. All right, that's number 24. Number 25 and 26 are 4th and 5th root functions, so I just got to graph the parent functions just once as we do these ones. So let's take a look. Number 25, we have f of x equals the 4th root of x, and g of x equals 2 times the 4th root of x plus 5 minus 4. There are 3 things going on in this transformation. Let's begin by actually just graphing the original. Do we have the original? Oh, wait, it's flipped over. So, oops. No, come on. I didn't copy that one, guys. Come on. I copied this one right here. Copy. Tell me you got it. All right. Okay. This software is not best. I adore it, but it has its moments. All right, this is the parent function. Over 1 up 1, over 16 up 2. We saw 4th root 1 earlier. So it goes quite the ways over just to go up. All right, there's your parent function. Now let's do g of x. So g of x has 3 things going on. A vertical stretch and 2 translations. By a factor of 2, which is good news for us, followed by a translation, 5 units left and 4 units down. from F. Okay, so let's start with that vertex, if you will, the -5, -4. We'll go 5 left and 4 down. Then we'll go over 1 to go up 1 doubled. And we'll go over 16 to go up 2 doubled. 16 away from -5 is +11. So we'll go over 16 to go up to 4 like that, doubled. And we'd have to go over 64 to go up 6. So we're not quite going to be able to fit that one. But we can at least get these ones here. Go up there, curve through that. And up and into that as we curve off. We're still going up very, very slowly because we can't get up to 6 doubled until we hit 64 away. I'm sure I could have made that curve significantly better. If you want to try and plot some points in between, again, be my guest, but it's still going that direction. All right, and then number 26. Oh, that looks interesting. I can speak more on this one depending on what we want to do with it. It's up to you. Number 26. We have f of x equals the 5th root of x, and g of x equals the 5th root of -32x plus 3. And as I said with the square root one with the negative inside, remember it doesn't matter with that whether that says negative or positive. It's still just a horizontal flip. We're just going left instead. But these graphs can go both left and right regardless. So let's first talk about, actually let's first graph the f of x and then we'll go from there. The f of x is tougher for me to kind of bring up here anyway because, you know, I don't know if I should be changing my scales or not. I think for the sake of whatever, I'm not going to. So we go over 1 to go up 1, but we'd have to go over 32 to go up 2, which you can't fit that. So really the idea of this that I'm just going to best do is just make sure you don't hit 2 yet. So it curves up and off like that. And don't get up to 2 yet. This thing's really got to go out. And I'm not even following my own advice. This thing's really got to go out first this way before it even finds its way upward to 2. So I'm trying that. We're at 17 there. So giving that kind of appearance, right? Oh my gosh, I can't do this. I'm going to struggle with this one, guys. All right, that looks pretty good. All right, and then on this side as well for the 5th root. I'll start from over here so I know what my final destination is. It's like a maze. Sometimes I start from the end. All right, there's our 5th root function. Now we have to do something similar again. This one might prove easier for us, and I'll show you what I mean by this. It's interesting. First of all, let's describe it. We are, oh, this is locked. Hold on. We are doing 3 things. We are doing a reflection. The graph of G is a reflection in the y-axis from F and a horizontal compression by a factor of 1 over 32. Okay, of 1 over 32, followed by a translation 3 units up. Now I'm going to start with the translation, as I generally do, and I'm going to keep the other stuff in mind. So let's start 3 units up. It's out of the way of this one. Boom. Now it's going to go this direction, right? But instead of going left 1 to go up 1, it's got to go only left over 1 over 32 to go up 1. For your sake, guys, it's pretty much going to look like it's on the y-axis still. That's how little it goes that way. Now, normally we'd go over 32 to go up 2, but now we get to divide 32 by 2. So we have to just go over 1 to go up 2. So we actually get to plot a point right there, which is quite interesting. 3 to the 5th power. Now this is the part where I'm going to have trouble and I'm going to use a calculator. 3 to the 5th power is 243. So I got to go 243, but I got to divide by 32. We get to go over around 7.5. We get to go left 1, 2, 3, 4, 5, 6, 7 and a half. It's 7.59. 7.5 to go up 3. And let's see if we can fit one more. What's 4 to the 5th power? 1024. 1024 divided by 32 is, oh, that's 32. All right, well, we can't fit that one. We can't fit 4 to the 5th power with that. Anyway, we can fit those ones. And then it goes this way as well. That way. And then over 1 to go down 2. And then over 7.5 to go down. It's kind of excitable to go down 3 like that. So it's quite the interesting go there. Yeah, you still have to go over 32 to get up to the next point there. So the curve does eventually hit rather extreme, but it takes a moment to get there. So quite the curve in here. Quite the curve in and quite the curve out. Okay, so like that. Now, what you could do with this, I'm going to move this down just a little bit before I move on to the next set. You could write that poorly. You could take the fifth root of negative 32 times the fifth root of x. You could separate them because the fifth root of negative 32 is 2. So you could take it as negative 2 times the fifth root of x plus 3. The only problem with this is I could only fit 1 point to myself instead of 3 points on either side of this thing. So this is now, it's a reflection in the x-axis, which is no change from reflection in y for fifth roots and whatever. But it's a vertical stretch by a factor of 2 instead of a horizontal compression by a factor of 1 over 32. So you would still fit these points. You would still be able to go left 1 and up 2 and right 1 and down 2. But those are the only points we could fit before we'd have to go over 32 to go up 4. Right? That's the next one that I wasn't able to fit and reach. So the first one was probably better with that, but it just goes to show that this is still the same thing. Guys, I've chugged a lot of water. Let me take a quick bathroom break. Hold on. All right, let's move forward. Okay. 27 and 28 are error analysis. Describe and correct the error in graphing f of x equals square root of x minus 2 minus 2. As far as our knowledge of transformations go, they went left 2 instead of right 2. The minus, we got to do opposite. So they should be down here. All right. I'll probably graph it there. I'll just do the same thing. So number 27. Excuse me. It's not like transformations are new to us, right? It's just a different kind of function we're doing it for. But the HK stuff is still the same. They translated 2 units left instead of right. Now, is the rest of the graph correct? It is. I'll show you that. Their translation down is correct as well, right? So let me copy and paste this graph. All right, so their graph is okay otherwise, right? Once they plotted this point, like their vertex, they go 1, 1, 4, 2, and that's all they can fit. So we're going to get the same graph here, only we're going to start down here, and we go 1, 1, and 1, 2, 3, 4, up to like that. Same graph, just translated over. And there's the fix. Okay. Number 28. Describe and correct the error in describing the transformation of this parent square root function represented by g of x. They said it's a horizontal shrink by a factor of 1/2 and it translated 3 units up. Their translation is correct. Their horizontal bit is incorrect. It's not a shrink. It is a stretch. Keep in mind things inside the function are treated as opposite of because of how it's affecting what you got to plug in for x. They described the horizontal stretch or the horizontal factor as a shrink instead of a stretch. Correction. The graph of G is a horizontal stretch by a factor of 2, ... The rest is as is. Remember, now your x values have to be twice as big to yield the same y values as before. That's why it's a stretch, not a shrink. Okay, let's move forward. Numbers 29 to 34. Let's see if we're graphing. Use a graphing calculator to graph the function, then identify the domain and range of the function. It's actually a good thing we're using a graphing calculator for this first one, for all of these that I'm looking at, because even I look at these and say, I don't know exactly what they'll look like. This ain't exactly the same vertex form of this. It's going to be quite the different look instead. It says then identify domain and range. Hey, we can use these graphs to do that, meaning the appearance of the graph. So I'm going to go straight into that right here. We are going to do y equals square root of x squared plus x, because who knows? I'm forgetful of what this can even really feature and look like, because it's going to be a rational function in some ways. It's not going to look like something I'm used to. Let's go and sketch the graph. Yeah, okay, so there's this. So I don't know if we're supposed to sketch the graph as well. I'm just probably going to copy and paste it over. So let me see what that does. So I'm going to copy and paste it over to this thing here. All right. Now, what we have to be very cautious of is what's going on in between here and here. It looks linear there, and it probably is, because we're taking the square root of an x squared and it becomes x. It's not straight up literally because there's other changes, right? It looks kind of absolute value-esque, and maybe there's that. But what else is happening? Range-wise, well, let's first talk about domain. Remember, x squared plus x has to be greater than or equal to 0. Greater than or equal to 0. If we factor an x out, it says x plus 1 has to be greater than or equal to 0. Now, this stuff gets a little tricky for us because what you actually want to do is treat this as a critical point, or find your critical points. Your critical points are 0 and -1. But it looks like based off this graph here that our domain says we can't plug in values that are between 0 and -1. So once we find out which way they go, it says apparently x has to be greater than or equal to 0, but less than or equal to -1 when it comes to our official domain answer. I can't speak too much onto why that is other than let's look at the graph and see how that looks. You can see that there's a little space in between. There's actually nothing graphed in between right here. And if you can make sense of that, you'd have to plug in a number between 0 and -1 to make sense of that, like -0.5. You'd get -0.5 squared, which is 0.25, minus 0.5, which is a negative number. And you can't take the square root of a negative number. Now, when you plug in 0, you do get 0 out. When you plug in -1, you do get 0 out. So the lowest value you get on here is y. So the domain is here. The range is y is greater than or equal to 0. Now, I could remove the axes from here as well, or I could go to the table of the graphing calculator, and we could also find those things out. So when I go to the table, you'll see that there are points that exist on these. But what if I plugged in values by increments of 0.5? I want to show you what it looks like when x is -0.5. Here's -1, right? What happens when it's -0.5? Error. You can't plug in a number between -1 and 0. You can plug in -1 and 0, and you get those out, and you can see that you get an error. Anything between -1, let's go by increments of 0.01. Anything between -1, actually by just 0.1. Anything between -1 and 0, sorry, hit the wrong button, will be an error because you can't take square roots of negatives. And then you hit 0 and you're good. Okay, so there's the first one, number 29, a little bit of exploration. Let's go back. Again, I'm not going to sketch these graphs. If you'd like to, go ahead. I'm just going to copy and paste them as we discuss them. Number 30, h of x equals the square root of x squared. You know, since we're doing several of these, 6 of them, I believe I might have to get deeper into the whole what I'm writing as domain here and critical points, but it's all based off the graph that you do. So with this one, we're going to go back into here and take square root of x squared minus 2x. Let's take a look at this graph. Now that I see what these graphs look like again, I can imagine what it will be. Excuse me. Okay, so there's this one here. Now this is the same kind of graph as we saw before. It's kind of absolute value-esque, only with a split on what you have. So this has this appearance here. All right, there's the graph. Now as far as domain goes, again, the graph's a little sketchy. No pun intended. But regarding domain, well, pun intended actually. Domain x squared minus 2x has to be greater than or equal to 0. Again, set it equal to 0 first to find out what your actual critical points are. Factor x out. And it looks like the x equals 0 and x equals 2 are your critical points. Now it looks like x actually hits 0 here. And then it goes to the left. And then x is 2, and then it goes to the right. So when x is 0, y is 0. When x is 2, y is 0. So your range is still bottoming out at 0. No change on there. Now, as far as your actual domain goes, it's going to be x can be greater than or equal to 0, and, excuse me, greater than or equal to 2. Let's start with 0. X can be less than or equal to 0, and x can be greater than or equal to 2. The range is y is greater than or equal to 0. Same thing if I explored the table of that. There would be errors anywhere in between. I mean, try 1. You can try 1 literally. 1 squared minus 2 times 1 is -1. You can't take the square root of a negative. And get it graphable. All right, number 31. F of x equals cube root of x squared plus x. It's at this stage that I will not know what it looks like, and I'm expecting some sort of rational function. No, I'm expecting some sort of... I don't know what I'm expecting. I haven't done this before. Maybe it's a square root function. I forgot. These aren't rationals. These are square roots. Cube roots. All right, let's do cube root. You can hit math. You can also raise it to the 1/3 power. But cube root of x squared plus x. See what this does. I'm going to change my window range, by the way. I prefer this one. And I'm serious. I prefer this one. All right, let's see. Yeah, a little curvy. Whoa, okay, okay. Now, one thing that I'm looking at here that I noticed, and again, I'm not going to draw it, just copy and paste it, but what I am noticing is, you know, your domain's going to be all real numbers. There's no restriction on these ones, unlike the x squared, the square root values, because you can take the cube root of anything and it'll still work out, right? There is a range limitation, though, and I'm curious to discover exactly what it is or how I discover it for myself, because it's normally graph-based that we have to figure it out. So I'll have to go back to the graphing calculator. We'll have to hit the min feature on it and see if we can figure out what it is. It looks like it's a number between 0 and -1. What is it exactly? I don't know. I literally don't know. Okay, so there's the graph. Domain is all real numbers. Range this time is limited, however, based on what's going on here. It's probably like the cube root of something squared. I don't really know. So let's go back to the graphing calculator. We're actually going to do the minimum feature this time. So we'll hit the minimum somewhere between, it looks like -1 and 1, -1 and 0 it's hitting. All right, so what's the minimum in between there? Look at that random-esque y value. Y can be greater than or equal to whatever that is. I'm going to round it, -0.630. I'll round to 3 decimal places, and even then it's -0.630. One can surmise that maybe that's some sort of, obviously, a cube root of some specific number. Maybe it's -0.5. Let me see what the cube root of -0.5 is. I'm very curious. And there's got to be some way that I should know what this is, and I don't know what that knowing is. So, you got me, the math teacher. I have no idea. No, it's not cube root of -0.5, so I don't know. I don't know. -0.5's cube root is -0.79 something. So it's something, and that's what we're going to work off from there. Use the minimum feature on the graphing calculator. Number 32. Interesting exploration of these. Because, like, what do we do off of these normally? Not much. I'm not saying that they're not relevant, but they're not. I don't know. Anyway, graphing calculator, we'll go back. Now, I used the cube root feature here before. Again, you can raise it to the 1/3 power. So this is, you can do 3x squared. Here's the equation, 3x squared minus x, and raise that whole quantity to the 1/3 power. And that's still the same thing as a cube root. There's no change there. Just make sure your 1/3 is also in parentheses like that, and then you're good to go. So let's see the graph. Probably more of the same kind of thing. Yeah, whoa. And it does something in between right there. Kind of bows in and out. Again, it'll have an all real number domain. There's nothing against anything I need to, I can plug in anything on X that I want. That's fine. But it does something there. It bottoms out at that little part. Again, no reason for me to actually know what that is. Maybe I should, but I don't. So we'll go to the graphing calculator. We'll figure out its minimum. Looks like it's between 0 and 1, though. Watch closer to 0. There it is. That y value. Oh, here's the x value, by the way. I should have looked at what the other x value was. So it looks like it was probably trying to be 0.16 repeating. I don't know if that's what it's trying to be, but guys, 0.16 repeating is 1/6. Is 1/6. So maybe there has something to do with these numbers that would represent a 1/6 for me. I should really go back to that other graph and see what the other x value was. I don't know why I wasn't looking at it before. Let me pause and see what the other x value was, then I'll come back to this. Okay, so I put in the other x value. Both graphs will be here, by the way. I put in the other x value, and the x value was -1/2. See, the calculator's kind of messing up on actually hitting it. I forgot I had to plug it into the function to take the cube root of it. So I don't know why those ones are being what they are. I'm got to think about them. There's got to be some connection there when I'm looking at the actual equations themselves. But the x value there seemed to be -1/2. So anyway, that doesn't affect the domain, but it does affect the range. So as far as me writing this range right here, previous one, I got to go fix it. Let me erase this other one and fix it one more time. Okay, so I got this one back here. Let's go to that guy. So again, that I'm guessing that's supposed to be 1/6, and then that's negative 0.437. So the domain, though, is still all real numbers for this one. So I'm going to write domain's all real numbers. Start trying to write in blue. Domain is all real numbers, and range, y is greater than or equal to negative 0.437. Or when you substitute 1/6 into here, it's the cube root of whatever that becomes. And I'm still interested as to why that is. I feel like I'm getting some sort of pattern that I'm picking up, but I'm probably going to lose it once we hit this constant one here with the +1. So I don't know if it's worth really bringing up or trying. Or is it easily, this, again, it's cube root. This is cube root of 3 times 1/6 squared minus 1/6. Then I don't know if I want to simplify what all that stuff is. So I don't know. I'll probably just leave it. I'm sure they're not doing anything particular like that. Okay, number 33. Number 33, we have f of x equals square root of 2x squared plus x plus 1. Okay, let's go ahead and calculate that one. I'm kind of having trouble with some of these, just kind of getting around them, because they're not quite in the realm of what we're doing. I know we're just plugging numbers in, but it's just weird to kind of talk about in this way of like, how does this connect to what we're doing? And I really want to get these domain range things going, right? And this is just a completely different looking kind of graph suddenly, right? So here we go. I don't know if there's a restriction in our domain this time, just because the plus 1 might prevent it from actually having a domain restriction, which I'm really interested in seeing. So let's copy and paste this graph. Yeah, that +1 changes things, because it's not just a normal +1, guys. It's not just translation 1 unit upward. This is inside the function. Okay, if we were speaking on, let's get to here. If we were thinking on setting this equal to 0 and solving for domain, stuff like that, there would be imaginary solutions. There wouldn't be any real solutions, so there aren't any critical points. So it looks like the graph literally is doing some form of absolute value and then kind of curves off and absolute values itself on the other side. Like that again. I don't think there's a domain restriction here. So domain looks like all real numbers in this case. Range, I think it's bottoming out at 1, right? If you plug in the smallest number you can plug into there, I guess the lowest number you get out is 1. I think if you plug in 0, I don't know. I'm going to hit that minimum. It'll be off screen. But minimum. No, minimum's less. Sorry. So minimum's this number here. I guess it is a little bit to the left, huh? So 0.935. Y is greater than or equal to that. And again, that's rounded. But that's what we're getting on this one. And again, I couldn't really tell you where it comes from. What's the x value? The x value is negative 0.25, so negative a quarter. Negative a quarter. You know where I'm sensing I'm getting these numbers from, by the way, for x, and I'm going to speculate on this next one for number 34 now that I'm seeing it. And I don't know why it is. I am at a loss, and I should look into it. But this first one, the x value was kind of at negative 1/2, right? Negative 0.5. I was trying to think of these numbers here, like, I don't know how to say what I'm going to say, but it's like this x makes me think of like a 1. So if I subtract 1 from there and then I divide by 2 times whatever this coefficient is here. I'm not saying negative b over 2a, but I'm saying negative b over 2a. I guess it wasn't this number. I guess it's negative b over 2a. You know what? I think it's negative b over 2a. I'm just connecting that now. I was thinking of this squared being a part of it. I don't think it's a squared. I think it sort of is. I think this is just negative b over 2a, because that would work here. That'd be negative 0.25. So on number 34, I'm going to make a guess before it even happens, okay? I'm going to make a guess. I don't know what the graph's going to look like. I'm going to guess where it bottoms out, though. So cube root of 1/2 x squared minus 3x plus 4. So I don't know what the graph looks like yet. Swear, I haven't looked at it. The well, the domain's going to be all real numbers, right? But as far as the range goes, it's based on plugging in a certain x value. So all real numbers. For my range, what I'm going to do, for my x, I'm going to put negative b over 2a. 2 times 1/2 is 1, so you get 3. I'm going to plug 3 into here, and I'm going to guess whatever that is when I plug it in will be my minimum y value. So 3 squared is 9, and that's 9 halves. And this is minus 9, which is negative 9 halves, plus 4. Negative 9 halves plus 8 halves is negative 1/2. I'm guessing the range will be y is greater than or equal to negative 1/2. That's my current speculation here. And I guess that makes a little bit of sense when I start actually thinking about what's going on with regard to a quadratic and stuff. Oh, cube root of negative 1/2. I'm sorry. So that actually that makes a lot of sense. That makes more sense than, I'm sorry, I never even thought about that. Now, what's the cube root of negative 1/2? I'm going to calculate that first before we do anything on this problem. So there's the old graph. The cube root of, where's cube root? Cube root of negative 1/2. This absolutely has to be it. Negative point. Oh, it's the number we were looking at before. We just didn't have to use it before. So I think we're going to look at this y value here. Y is going to be greater than or equal to negative 0.794. Okay? Let's go and type in the equation and see if that's going to be it. And I don't know what the graph's going to look like, though. 1/2 x squared minus 3x plus 4. Whoops, there's no plus there. Plus 4. Now, the plus 4 is going to change some things on the graph, I guess. I don't think it changes the... Oh, it might have changed things. Is this a cube root? Oh, this isn't a cube root. Cube root of... The plus 4 might change some things as well. I don't think that's the minimum. I think the plus 4 changed things. We'll see, though. We'll see. All right. So there's the graph. Let's copy paste it. So sorry if some of this stuff seems like a time waste. I'm using this just as much for learning and exploration as you guys are. I hope that's okay. Maybe that is negative 0.79, though. It's just shifted over. It's no longer the same x value. That's the only thing. Okay. Let's go ahead and figure out what that actual range is, because this was just a guess. So let's go to the graphing calculator. Let's do minimum. It looks like it's at x equals 3. So let's go from 0 to 5. Let's find that min. It's that y value. Now, I don't know how the minimum's achieved as a for sure on that 3. Obviously, it has to do with the 4 being in there. But I was right. That was negative 1. The cube root of negative 1/2. So anyway, so that's y is greater than or equal to. I'm still going to use the rounded values. I don't think they expect you to notice that. Oh, 794. I don't think they expect you to notice all that I was talking about there, because I barely noticed it. But we're going to use it. All right, let's get to move forward on things that we probably should know a little more about. Abstract reasoning. In exercises 35 to 38, complete the statement with sometimes, always, or never. Now, I haven't done one of these sets in a long time, but the one thing I'll state on these is, if you don't know, don't guess sometimes. It's not one of those if you don't know, guess C things. Sometimes is the one that you would guess if you know for sure a case when it does work and for sure a case when it doesn't work. Otherwise, guess always for like, this is a case when I know it's always, and otherwise guess never when I never know when it's going to be true. So the domain of the function y equals a times the square root of x is always, sometimes, or never. I should probably type these. Always, sometimes, or never, x is greater than or equal to 0. The domain of the function y equals a times the, where's that symbol? Square root. Oh, I know this will look a little bit different like that. Unfortunately, I can't do anything more with that. Is, that's always x is greater than or equal to 0. As far as domain goes, I have this symbol here, greater than or equal to 0. So it's always for that one. Doesn't say explain, but my basic explanation is we're talking about domain. There's nothing that's affecting the inner portion of the function. A doesn't affect the inner portion of the function. We're still going to the right from 0 onward. 0 is the smallest number for x I can plug in and still get a value out for y, and then they go positive from there. Number 36, the range. It's the same. I'm not saying it's the same answer, but it's the same text as this previous one here, so I'm going to get that ready. Range of the function. It's not always y is greater than or equal to 0, because this one depends on a. If a was a negative number, then it would be going downward. So this is a sometimes case. This is a case where if it was literally a negative a value, it would be y is less than or equal to 0. A isn't equal to 0 in these cases. Otherwise, it's no longer a square root function, but even then, it would still be a sometimes. So I'm not really considering that one. Number 37. All right, I might have to copy these ones in, not just type them, because the information gets a little tricky to type out. I could literally just say the words, but I want you to see the things in context. So sorry about this. I'm doing these on the fly. Number 37, the domain and range of the function are of a cube root are blank all real numbers. For a cube root, it's always all real numbers. Cube root functions have no restriction on domain and no restriction on range. Number 38, the domain of the function y equals a times the square root of negative x plus k is blank x is greater than or equal to 0. That's never. Notice now this time this is, I have to drink water. This is a reflection in the y-axis. It's going from here to here. So it's flipping it over that way. Now we're going to the left, not to the right. This one's never. Let me fix my hiccups. Okay, you'd think I'd learn to not eat massive meals before doing videos. I haven't. I always assumed the videos would go long, so I got to really chow down beforehand. Clearly not as much as I ate 2.75 pounds of cheesesteak and fries. All right, number 39. Problem solving. The distance in miles a pilot can see to the horizon can be approximated by this function here, where n is the plane's altitude in feet above sea level on Earth. The function m of n equals 0.75 times e to the n approximates the distance a pilot can see to the horizon in n feet above the surface of Mars. That's because Mars has more curvature because it's a smaller planet, because planets are not flat. Sorry. Okay, anyway. Write a rule for m. What's the distance a pilot can see to the horizon from an altitude of 10,000 feet above Mars? So it's a pretty straightforward process, guys. We got e of n equals 1.22 times the square root of n, and m of n equals 0.75 times e to the n. So we are going to substitute that function into here. It's basically a vertical compression by a factor of 0.75 or 3/4. 0.75 times 1.22 times the square root of n. So I got to do 3/4 of 1.22. 1.22 times 0.75. We'll simplify that, and we get 0.915. So m of n equals 0.915 times the square root of n. So on Mars, if we have the altitude, if we have an altitude of 10,000 feet above Mars, we're going to be able to see it by plugging that in. So m of 10,000 equals 0.915 times the square root of 10,000. Square root of 10,000, that's 100, right? So this, I think this answer is going to be 91.5. So times square root of 10,000, yes, 91.5. So equals, and this is exact, 91.5, this is in feet, this is in feet, feet. What's the distance a pilot can see to the horizon from an altitude of 10,000 feet above Mars? They can see 91.5 feet. What does that mean? The altitude, I was hearing it the other way. They can only see 91.5. Oh, this is miles. I'm like, why would this be feet? That makes no sense. Okay, that makes so much more sense. I was like, I don't understand the question suddenly. That's miles. Okay, 10,000 is in feet. That's in miles. I got it. I feel much better about the problem. I was going to say, if I'm 10,000 feet in the air and the farthest I can see is 91.5 feet out, something is really wrong. 91.5 miles. Much better. Okay. Great. Number 40. The speed in knots of sound waves in air can be modeled by that funky function there, where K is the temperature in Kelvin. The speed in meters per second of sound waves in air can be modeled by that. Write a rule for S. What's the speed in meters of sound waves, etc. It's probably a lot like number 35 or 39. We are just doing a substitution. Let me write out the initial information to begin with, though. 643.855 times the square root of K over 273.15. Now, I don't know the stuff scientifically. I do know that 273.15 degrees Celsius is 0 degrees Kelvin. No, I have it the other way. This many degrees Kelvin is 0 degrees Celsius. Ah, shoot, I don't know. It's one or the other. I do know that there's just an addition or subtraction conversion of that. Anyway, I'm not a scientist, guys. I know that absolute zero is, it must be 0 Kelvin is absolute zero, right? Coldest, you can have it. Anyway, V of K over 1.944. We're going to substitute this in place of V of K right there. So it's going to look a little funky, but hopefully this division will either clear up or we're just going to have to leave the fraction just like that. So S of K equals 643.855 over 1.944 times the square root of K over 273.15. Now don't try and clean up anything inside here, right? We'll just leave it like that. I just want to see if those two other numbers can divide evenly. I'm going to guess not, but maybe a little bit. If it's still an exact decimal, I'll go ahead and write it. 1.944. Yeah, no, it's something funky. But I still need to use it in my calculation anyway, right? So now we're going to do 305 Kelvin. So S of 305 equals, and I'm just going to plug 305 into there, right? So I'm going to the calculator. I started to do this division right here. All right, this is this number divided by that number. Now we'll do that times the square root of 305 Kelvin divided by 273.15. And there's an answer that we're getting right there. 349.978, about 350. This is in meters per second. This is the speed of sound waves at this temperature. Okay, so I guess it does make sense that 273.15 degrees Kelvin is 0 degrees Celsius. Because maybe at 273.5 at freezing point of water, then it's some speed of sound, whatever. Anyway, so S of 305 is about 350. I'm rounding this one. About 350 meters per second. Meters per second. Okay. Numbers 41 to 44. Write a rule for G described by the transformations of the graph of F. Let G be a vertical stretch by a factor of 2, followed by a translation 2 units up of the graph of F of X equals square root of X plus 3. The plus 3 is on the outside. So vertical stretch by a factor of 2, followed by a translation 2 units up. Up 2. So G of X, we're going to double that of our F of X, and then we will add 2 to the whole set. So G of X will equal 2 times here, the square root of X plus 3. We have to double even the plus 3, and then we'll add 2 on the outside of that. Okay? We're stretching everything from there. So that's 2 root X plus 6, and then the plus 2 on the outside, which is 2 root X plus 8. There's our G of X graph, or equation. Number 42, and we're not graphing. Number 42. G be a reflection in the y-axis followed by a translation 1 unit right of the graph of this equation, 2 times the cube root of x minus 1. So we're going to go reflection across y-axis followed by a translation 1 unit right. Right 1. Okay. So for this one, our G of X equation, reflection of the y-axis means make the x's negative inside your function. And, okay, let's start with this. Let's not start with G of X. Let's start with H of X. Normally I like to do this in a different color here, so let's do some blue. Let's start with this one. So with this one, this will be 2 times the cube root of negative x minus 1, like that. Now, whether you choose to factor it or not is going to be up to you. But the important part about this you have to do is, now that we get to our G of X, we're going to go 1 unit to the right. That means we're going to take our h of x. But inside of there, we have to do 1 unit right, which is minus 1. That means minus 1 is going to replace x. So it's going to look like this. We're going to do 2 times the cube root of negative, and here's our new x, and then there's a minus 1 as well that's on the outside. This is an answer. It's nobody's favorite answer here, so I'm going to work on distribution. This is 2 times the cube root of, distribute the negative x plus 1, and there's minus 1. 1 minus 1 is 0. Those go away, and this is 2 times the cube root of negative x. That's an answer. I'd prefer taking the cube root of negative 1, pulling it to the outside, and writing it like this, negative 2 times the cube root of x. You have to keep in mind that horizontal changes are the same as vertical ones. The only one thing is, because it had a minus 1 on the inside to begin with, it only affected the x, right? But the minus 1 is still there. So there are some things that are different here with horizontal reflections versus vertical reflections, or over y versus over x, when the minus 1 is already inside of there. But now that it's taken care of, you can factor it out. Okay, one or the other. Number 43. Let g be a horizontal shrink by a factor of 2/3. Ooh, that's a little tricky. Followed by a translation 4 units left of the graph of f of x equals square root of 6x. I don't know what I was writing. Okay, we're going to go horizontal compression by a factor of 2/3, followed by a translation 4 units left. Let's start with the horizontal compression and then move on from there. So we're going to take our f of x equation. We don't write 2/3 inside here. We write its reciprocal of 3/2, right? So we're going to be taking the square root of 6 times 3/2 x. 6 times 3/2 is 9. So we are going to get the square root of 9x. Now, if I were a simplifying lad, which I am, I'd love to take the square root of 9 right now and turn it into a 3 on the outside. I much prefer this appearance, and it's not affecting x on the inside anymore. So as far as g of x goes now, we can take our h of x and we can go left 4. So we have x plus 4 like that. So this will now be 3 times the square root of x plus 4, and that can be our final answer. Now, one version of the answer can also be from here, g of x equals the square root of 9 times the quantity x plus 4. And if you clean that up by distribution, it would be the square root of 9x plus 36. Now, even if you had the simplified version like that, I actually much prefer this one because this shows the true h value of negative 4. We're going to go 4 left, not 36 to the left. I like this one the most, though. This is my favorite one, even in graphing form. I much prefer vertical stretches than I do horizontal compressions, especially by a factor of 9. And especially when you can't tell, do I go left 4 or left 36? The answer is left 4. Anyway, number 44. Let g be a translation 1 unit down and 5 units right. Oh, look at that original equation. Followed by a reflection in the x-axis of this graph here. So we got f of x equals negative 1/2 times the 4th root of x plus 32. 3/2. 3/2. This is one you definitely want to do one part at a time, or let's do the translations together to begin with, but you definitely want to do them before the reflection just because you don't want to make a mistake on that part. Let me write them though. You're going down 1, right 5, and then you're going reflect across x-axis like that. Okay, so down 1, we're taking our f of x and we're going down 1. Right 5 is like that. We'll start with these two. So h of x equals, this will be negative 1/2 times the 4th root of, you substitute x minus 5 in for x, and we have plus 3/2, and we subtract 1 from that whole thing. So it looks like we got to do 3/2 minus 1 as a whole. That's the only thing that actually I can change inside here. Negative 1/2 times the 4th root of x minus 5, and instead of plus 3/2, it's actually plus 1/2. 3/2 minus 2/2 is 1/2, and there's that portion. Now we're going to do a reflection in the x-axis. So for this one, we have to do g of x equals negative h of x. Reflection in the x-axis is flipping over the y values. So we're going to flip everything here over. We're going to take the opposite of this whole thing, like that, which means distributing the negative, which means that first portion is going to be positive. This will be a positive 1/2. This inside stays the same. There's no change there. And this is minus 1/2 there. So not much to make this look cool. It still looks ugly as an equation. It's probably fine to graph, but that's it. Okay, numbers 45 and 46, write a rule for G. We have to identify kind of what's going on here. I'm definitely going to copy and paste this and find some reference points, see what's going on. So writing a rule is coming up with the equation based off of the parent function. So on number 45, our original parent function is that absolute value of x, okay? Notice that it is based off of our origin. We got 1, 1, and 4, 2, and stuff like that. Now, G looks like a translation 1 unit to the left. So if there's one thing that we do know is there's going to be an x plus 1 inside of our function. What else is happening? There's no sort of flipping over of any kind. It looks like a stretch. Instead of over 1 up 1, we're going over 1 up 2. Instead of going over 4 up 2, we're going over 4 up 4, which to me means there's a vertical stretch factor of 2. So we're going left 1, and we're going vertical stretch factor of 2. So for me, G of x is 2 times the square root of x plus 1. 1 left means the x plus 1 is inside the function like that. That's the appearance of the graph to me. If I were to graph it, if I were to have that graph, that's the equation I'd have. That's the way I'm seeing it. Now, number 46 says, well, let's copy and paste it. We got a cube root function, and then our G looks to be some flipped over version of that. Now, the first thing I want to refer to is that reference point. If you can represent where that center is, that'll be good. So you can see, first of all, you can see how their graphs clearly do cube roots significantly better than I've been doing. I've been terrible with them. But there's their center. You go 1, 1, you go over 8 up 2, and there's that. Now, our G function looks to be centered right there at 2, 0, which means it did translate 2 units to the right. We're going right 2 units, but normally that comes after any vertical stretches and reflections and stuff. Now, this graph's going this way instead of the other way, which you can say that in one of 2 ways. You can either reflect over the y-axis or reflect over the x-axis. Both are interchangeably the same. There's more than one correct answer for this. I prefer saying reflect over the x-axis in terms of changing the y, flipping that over. Either is fine here. It doesn't look like there's a change in scale. It's left 1 up 1. So there's no change in scale by that. So it's just as simple to us as G of x equals negative cube root of, and we have x minus 2 inside of here. An alternative version of it is this. Instead of having the negative on the outside, you can have it on the inside. But where you have to be careful is the x minus 2 would still be a quantity like that. If you want to write it like that, fine. If you want to distribute the negative, fine. If they have a distributed version, it would be looking like that. This is probably what they'd be writing. It's a trickier one to graph off of. I don't recommend it. I really recommend this one right here as a whole, not just by graphing, but by writing the equation. But this is acceptable. So is this. It's just not simplified. There are parentheses there. But this still means 2 to the right, like that. Remember, cube roots can kind of penetrate negatives inside of their functions, whereas square roots cannot. Reflecting over x and y are the same thing for a cube root function. All right, numbers 47 to 50. Write a rule for G that represents the indicated transformation of the graph of f. Okay, well, this one looks a little less involved than the ones we did right before the graphing ones because we're being told specifically what to do here. So, G of x equals f of x plus 3, unless we're asked to graph. Oh, write a rule. Does that mean we describe it, or does that mean we make the equation? I think it says write the rule. It doesn't say describe. Oh, the problems get a little more complex as we go. I see. Okay. So, okay. G of x, we just take, and I think we got to simplify it based on what I saw in the thing, but x plus 3 plugs in for x, and honestly, that's it. There's nothing else we got to do in the problem. So 47 starts you off basic. Number 48. Number 48. Here's our original f of x. And here's our g of x. Okay, so for g of x, we're going to take the opposite of our f of x. Here's our f of x. And then we're going to add 9 to the result. So the 9 doesn't get the negative distributed into it, so it's basically negative 1/3 times square root of x minus 1, and then the plus 9 is after, and that's the result of g of x. Flipping it over, translating 9 units up. Number 49 and 50 have a little bit more involvement, especially with regard to what's going on inside of there. F of x equals negative square root of x squared minus 2. Let g of x equals negative 2 times f of x plus 5. Okay, so two things are going on in there because they have them already set up. Let's try and do both at the same time. So we are going to do negative 2 times our function. But in our function, we're going to replace x with x plus 5. So there's a negative here. There's square root of x plus 5 is taking x's place, like that. Oh, and that's it. And that's it. But we still have more to clean up here. So first of all, the negative 2 times negative 1 is a positive 2. And there's the change there. Nothing else, but there's no negative on the outside. We got to expand this. This will be x squared plus 10x plus 25. Now 25 minus 2 is 23. Do you mind if I change that to a 23? I'm going to change it to a 23. And that's a 23 right there. And we all the same. It's all good. All right, number 50. And don't try and clean anything up inside there. That's just a weird looking graph, right? It's a weird duck. F of x equals the cube root of x squared plus 10x. G of x is 1/4 times f of negative x plus 6. Okay, so g of x, we're going to take 1/4 of all that is our f of x, which is, I guess it's just this whole thing. So I can just do this straight up like that. Inside of x, instead of x, I'm going to write negative x. So negative x squared plus 10 times negative x. On the outside of our entire function, we're going to write a plus 6. So it looks like really the only thing I need to change is just what's inside. The outside has no real change. So actually, for this, I'm just going to put that in parentheses like we didn't know what to do yet. But now we do. Now it's 1/4 just times that. So 1/4 times the cube root of negative x quantity squared is x squared. 10 times negative x is negative 10x. And then plus 6 is like that. And there it is. All right, numbers 51 to 56. Use a graphing calculator to graph the equation of the parabola. Identify the vertex and the direction the parabola opens. It's kind of interesting in the way that we did do some of these things in IM2. It didn't start off looking like these as equations. Well, it sort of did. We graphed x equals y squared's equation. So I could tell you what these graphs look like without a graphing calculator. But I think the goal is to make this thing solvable. We're treating this chapters on radicals, right? So we want to play with the radical format. I think that's more of the idea. It doesn't matter that you've done these before in that way. First thing you want to do is multiply both sides by 4. Our goal is to solve for y because we want to be able to write this in our graphing calculator, which are y equals equations. So we're going to take the square root of both sides like that, and now we're going to have y equals plus or minus root 4x. But the thing about the square root of 4 is it's 2, and I'd love to simplify that instead. And the thing is, these are really two different equations to us. So this is going to be y1 equals positive 2 root x, and y2 equals negative 2 times square root of x. And in total, what you're going to see is a sideways parabola. I'm going to tell you right now, guys, this graph is going to look like something that's going to open up to the right. It's going to be, the only thing is I can't tell here. I'm trying to think if it's going to be a little, I think it's going to be a little fat. Yeah, it's going to be a little fat like that and look that direction. So expect to see that kind of graph here. We're going to go to the graphing calculator and check them out, but we got to plug them into two equations. Okay, so we're going to get here, get 2 root x and negative 2 root x. And again, together they make one complete parabola, rightward facing. It goes and like that. So that's one full parabola. It is sideways facing, rightwards facing. They said use the graphing calculator to graph the equation. Again, I'm not going to sketch these. Okay, I'm just gonna copy and paste them. They said use the graphing calculator, so I'm gonna let it do the job for me. There's the graph of it for domain and range. identify the vertex and the direction. Sorry, they don't want domain range. The vertex is at the origin, and the direction it opens right. Did I know that? Yeah. We're good. All right, number 52. 3y squared equals x. We're going to divide both sides by 3 this time. This y squared equals, I'm going to write 1/3 x. We kind of tend to see our compression factors, stretch factors, things like that in this way. Take the square root of both sides. And now we'll get y equals plus or minus the square root of 1/3 x. 1/3 is not a perfect square, so I'm going to leave it inside there this time. So our two different equations we're going to write are y1 equals positive 1/3 x and y sub 2 equals, or whatever, negative root 1/3 x. So let's get those two graphed. Same biz. It's going to be opening up to the right with the vertex at the origin. So we got square root of 1/3 x and square root of negative 1/3 x. You don't need parentheses around the 1/3 here specifically. Order of operations will apply. I didn't put a negative though. That would have been just the same graph twice, and I just said, where's the bottom? Oh yeah, I didn't type something in. Come on, you idiot. All right, so to open up this way, a little sharper, significantly sharper rather. But that's because it has a horizontal stretch by a factor of 3. That's what the 1/3 is telling you. So, there it is. All right, vertex is once again at the origin, and it opens to the right. Okay. Sorry, I had to pause and watch the end of the Giants game there, or rather, watch the Giants win. So that was an exciting one. Maybe you'll see a replay in the background. It was very nice. All right, number 53. Negative 8y squared plus 2 equals x. Okay, once again, our goal is to get y by itself. Let's subtract 2 from both sides to begin with. Now let's, we'll divide by negative 8, but I'm rather going to say let's multiply by negative 1/8. Because what I'd prefer is really the best graphing form of this, right? Negative 1/8 like that. I'm not going to distribute it. I'm just going to kind of make it better looking. This is a personal preference thing. Listen, we're doing this in the graphing calculator. What you want to do is up to you. I want to predict what some of these answers will look like before we actually see them. And if you want them in their best graphing form, you'd want this factored on the outside of that to begin with anyway. No full distribution. Just like that's actually one of the better forms of what you do here. And take the square root of both sides, you get plus or minus the square root of negative 1/8 times x minus 2. Again, when all's said and done, when it comes to graphing for me, what I know is this. This graph is going to go 2 to the right. It's going to be horizontally stretched by a factor of 8, and it's going to be reflected across the x-axis. If we want to talk about what this graph's going to look like before I even use the graphing calculator on it, the vertex is going to be at 2, 0. And this graph is going to open to the left, and rather sharply. It's going to be a, leftwards facing parabola like that. So what I will do here, let's go to the graphing calculator. Let's plug in that equation. And you can do it in whatever form you want. I'm going to plug it into the exact form I had. Remember, there's a plus square root of negative 1/8 times x minus 2 and negative square root of negative 1/8 times x minus 2. Okay, so the graph should be at 2, 0, going very sharp, and going to the left. And there it is. There's your parabola. So again, that's what I was expecting for it based on my graphing form, if I'm still going to get some practice for myself as far as, hey, how would I know what it looks like beforehand? Well, you get it in a graphing form. If you're really good at your HK stuff, this is what you'd be doing on it. And so instead of dividing by negative 8, and by the way, I don't want a negative in the denominator. So there's that as well. All right, number 54. Do you guys see the replay, by the way? Number 54. 2y squared equals x minus 4. More of the same. We'll divide by 2, but it's also the same thing as multiplying by 1/2. So for me, I'd rather write it like this. So we're going to have plus or minus the square root of 1/2 times x minus 4. Now, by the way, before I end up graphing it, why am I not pulling out this 1/2 from here? Well, I'd have to take its square root, and 1/2's not a perfect square of anything. Neither was 1/8. Neither was 1/3. I might have mentioned it for that one. I can't remember because the Giants game thing finished. But 4 is a perfect square of 2, right? If this had 1/4 or 1/9, I'd pull it out. Square root of 1/4 is 1/2. Square root of 1/9 is 1/3. I would pull that one out of there. But as long as it's not a perfect square, I'll leave it inside there. It's a stretch by a factor of 2, a horizontal one. So this vertex should go to 4, 0. This thing is going to open to the right, and it's going to be twice as sharp. It's twice as stretched as it normally would be. So let's go to the graphing calculator and take a look at those ones. This will be square. The only problem is I have to just keep retyping these over and over, and you probably do have to as well. So 1/2 times x. That's not an x. That's a times sign. X minus 4, and then negative square root of 1/2 times x menos 4. So there it is at 4, 0, and it's opening to the right. There's your graph. Again, a rightwards facing parabola, and we need both equations for that to actually show up. All right, 2 more. Number 55. X plus 8 equals 1/5 y squared. 55. We have to multiply both sides by 5. I'm going to put the y squared on this side. That's 5. You might say 5x plus 40, but once again, if you were going into an actual graphing form, I'd actually prefer it on the outside anyway. So this is horizontally compressed by a factor of 5. Again, well, here, let's do this. I'll write it as plus or minus square root of 5x plus 40, and we will write that in the graphing calculator. But where's the vertex going to be? Is it going to be at negative 8, 0 or negative 40, 0? It's going to be at negative 8, 0. Okay, it's going to be vertically compressed by, or horizontally compressed by a factor of 1/5, so it's going to be a taller graph like that, and it's going to open to the right. So if you're trusting what I'm saying, I want to show you that even when I type in this equation, it's going to be saying that. So let's go into, or if you're not trusting, have at it, right? So we're going to do square root of, let's write 5x plus 40. Game on. And then here, negative square root of 5x plus 40. Like so. And this will open to the right, vertex of negative 8, 0, and it's going to be a taller look of a parabola, rightward facing parabola. This is negative 8, 0, right there, a taller parabola like that, and there it is, right? So that's what that thing is. That's how that takes on its form. That's why I'm saying a factored out version of the 5 is better than not. That's why those forms appear that way. Do not distribute into the h unless you plan on doing that. Let's take this even one step further, guys. We're talking about domains. The inside needs to be greater than or equal to 0. 5x plus 40 needs to be greater than or equal to 0. That's your domain. So we subtract 40 and divide by 5. X has to be greater than or equal to negative 8. We're going to do a lot of this stuff when we talk logarithms. Is that the next chapter? It might be chapter 5. When we talk logarithms, we're going to have to do a lot of domain stuff like this. So this, once again, tells you a little bit more about your domain. It has nothing to do with the 40, per se. All right, and number 56, 1/2 x equals y squared minus 4. 56, 1/2 x equals y squared minus 4. Once more, well, I don't know. I'm going to add 4 to both sides. Now, before I take the square root, this is one of those instances where if I wanted to predict what the answer would be beforehand, guys, I would factor a 1/2 out of this. 1/2, and then this would be x plus 8. Remember, 1/2 times 8 is 4. So if I factor it out like that, that would help me in my own sense of understanding what this graph would look like for myself. This parabola. Again, is your vertex going to be, because you could do square root right here as well, is your vertex going to be at negative 4, 0 or negative 8, 0? It's going to be at negative 8, 0. Your vertex is going to be at negative 8, 0. It's going to open right. Horizontal stretch by a factor of 2, so it's going to be a little bit sharper. All right, so let's go ahead and take a look at that one. I can even write the one that would have said the 1/2 x plus 4 there, but no parentheses around the x plus 4. So I'll do square root of 1/2 x plus 4, but the vertex is not going to be at negative 4, 0. It'll be at negative 8, 0. 1 half x plus 4, like that. Whoops, they need a plus 4. Okay, so at negative 8, 0, boom, like that, kind of sharper parabola opening to the right. And there you have it. So hopefully you're getting a good sense of what these answers could be predicted as, or how we could still write it in graphing form. Like I stated, though, we have been doing, you graphed these in IM2 perhaps in a certain section where you did focus and directrix and things like that, but you wanted to actually get x by itself. Now we're finding a way to get, this is a radical section, so graphing it like that, hey, it has relevance. I want to give this relevance. And by stating what I stated, I think I did. All right, next exercise is 57. In exercises 57 to 62, use the graphing calculator to graph the equation of the circle. Identify the center, radius, and intercepts. Now, again, you might have graphed circles in IM2 in chapter 10. I think it was chapter 10. I think it was section 10.7. I want to try and be very specific. I think it was section 10.7. To give you a predictive answer, if you know the form of this stuff, the center, this case, will be at the origin, and the radius will be 3. But we're going to do this based off the graphing calculator, and in order to do that, we still have to get y by itself. So we're going to subtract x squared, and we're going to take the square root of both sides. So y is plus or minus square root of 9 minus x squared. So you have two equations here, and do not try and simplify that. You're fine the way it is. We're positive square root of 9 minus x squared, negative square root of 9 minus x squared are your two equations. So we'll go into here. Y equals positive square root of 9 minus x squared. And y equals negative square root of 9 minus x squared. Okay, a circle with a radius of 3. Top half, bottom half. And there you have it. Center at the origin, by the way. So there you have it. It's number 57. Okay, number 58. X squared plus y squared equals 4. Once again, do you understand why this was 3 based off the 9? Because that's actually what it's related to. Have you done these before? I'm not sure. Your center here should be at the origin once again, but this radius this time will be 2. Okay, we will be subtracting x squared from both sides, and we will take the square root of both sides. Do not ignore the plus or minus. Remember, these are not functions. Circles aren't functions. These are two different equations that we got to write out. We'll get the graph for it. Same exact stuff as we had previously, only instead of a 9, we have a 4. So this is a 4 minus x squared, and opposite of, or square root, 4 minus x squared. Radius is 2 this time. A little bit smaller. Center still at the origin, though. Let us copy and paste. Let us bow our heads in prayer to the circle with the center and radius. I'll probably bring this information over here. That's a little more fitting. All right, there was that one and this one here. Okay, number 59. Well, this one, it's a little wonkier as far as without me actually writing it in standard form of the equation to tell you exactly what it is. I think I can see the information for what it is. But because it's already squared, I guess we just do the square root straight up. I guess we're good there. If I were to speculate, the center would be at 1, 0, and the radius would be 8. I believe it's supposed to be that. Anyway, we just got to take the square root of both sides here. Plus or minus square root of 64 minus x minus 1 quantity squared. I don't think they want you to expand that or anything. You're good. Once y's by itself, we're all straightforward. We're squared away. That's fine. So as far as this equation goes, we'll write those two together. We'll get y equals square root of 64 minus, and this needs to be in parentheses, x minus 1 quantity squared. Unless you expand it and you take care of that. Oh, I want to do the squared button. It's fancier, huh? And then negative square root of that. Okay, so I should have this time a center at the origin and a radius of 8. My problem is my window range. It's a little too small. So I'm going to go back to the negative. See, okay, this thing's going to be a little small on the top and bottom. I want to show you that first. It's going to be a little small on the top and bottom. Now, you might say, now, by the way, the center, by the way, is now at 1, 0. Remember how I mentioned that, right? It's at 1, 0. You can tell that it's a little, shifted over. I'm a little at odds with what I want to say here regarding, okay, if I go to window range, right? If I change this from negative 10 to 10, here's the problem about, this is why I like what I typed in more. Because this will not show a perfect circle anymore. It'll show the circle, but it will look more, I think, stretched. I think it'll look more stretched. It'll look more skewed in one way. Not only that, it doesn't connect the top and bottom. It's supposed to connect the top and bottom. The graph just fails to do vertical lines, but it doesn't look like a circle anymore, right? Because the window range. So what I know about this trick and these numbers, and I remember this from back in high school, these numbers here for a TI-83, and not all the calculators do this, I want to state that right now, not all the calculators do this, is this exact proportionality is perfect for these numbers. Now, if I grow these 1.5 times bigger, like if I turn this into negative and positive 9.3, then, okay, the numbers will fit. And then that means I need to make these that many times bigger, so plus 4.7 is 14.1. So negative 14.1 and positive 14.1. So let's see what this does. Okay, it won't complete the circle, unfortunately, as well. I think once you zoom out too much, it doesn't want to do it. It's close, but it looks like a circle again, right? Now, where's the circle center? It is at, I can't get it exactly, but it's at 1, 0. You can see it's a little off center, and that's something that I think you have to know something about graphing form for it. Anyway, the radius is 8. Radius is 8. Oh, let's copy and paste it. Yeah, I don't know what they expect you to do as far as like, well, you have to know a little bit about your calculator or about equations of circles, which you might already know, in order to fully get that answer, because discovery of this graph in that form cannot guarantee that you're going to get what you want out of it. Okay, and 61 and 62 will be mean when it comes to center, especially if you're just speculating. So number 60 is 1 minus y plus 3 quantity squared equals x squared. All right, we have a few things to get y by itself here. So this will be, I'm going to add y plus 3 squared over. So I'm going to add y plus 3 squared over, and I'm going to subtract x squared over. So now it's going to be 1 minus x squared. They basically switch places. And then I can take the square root of both sides. Y plus 3 equals plus or minus the square root. This will be an interesting looking equation. And then subtract 3. Y equals negative 3 plus or minus the square root of 1 minus x squared. If I saw this straight up, I'd say, well, I don't know what to do with that. Actually, let's put it on this side here to make it look more like the vertex form kind of graphs that we know how to do. So there's a positive root 1 minus x squared minus 3. Never mind. We'll leave it like this. Okay. So here are the two equations we're going to be writing out. Now, looking at this equation, I believe we do have a center at 0, negative 3, and a radius of 1. So when I go to the graphing calculator, I am going to reset my window range to my preferred here. It's the only ones that seem to give me circles that seem to complete themselves. And I need to type in those equations. So there's going to be negative 3 plus the square root of 1 minus x squared. And there's negative 3 minus the square root of 1 minus x squared. Now again, I'm predicting a center at 0, negative 3, and a radius of 1. Going 1 around this. There you go. The little guy, the little guy. So there's this graph. And that seems to be the information that lines up. Okay, two more of these. Number 61. X squared plus y squared plus 12x minus 13 equals 0. Now this will require me to do mental math unless I plan on completing the square when it comes to the actual information. I'm going to first solve it the way they want us to, which is take all these things over to that other side. You know what's interesting about this though is this can factor. I don't think it's worth. See, I'm looking at the x information. I'm looking at this and saying you can factor this into, although we could complete the square as well. But this factors into x plus 13 times x minus 1. I don't think that matters for us too much. Oh, they wanted intercepts, didn't they? Ooh, I missed information on every question. Uh-oh. Well, we have the graphs, and I'll tell you what. Without the graphs, I wouldn't be able to know those intercepts, except that when I started to factor, I think we're going to know those intercepts pretty soon. Okay, I'm so sorry. I missed those. Okay, x-intercepts. I'm so used to just center and radius. X-intercepts here were -3 and 3. Y-intercepts were -3 and 3. I'm sorry about this. Okay, these ones, x-intercepts were -2 and 2. Y-intercepts were -2 and 2. Now, when it comes to the radius, see, the intercepts have to do with the radius, right? And your center. If your center's at 1, 0, and your radius is 8, you're going to go 8 up from 0 and 8 down from 0. Oh, I'm sorry, those aren't intercepts. Oh, we have to get all of our intercepts. Uh-oh. These intercepts aren't going to be very pleasant over on these guys. I could use Pythagorean theorem and figure them out for you. I got to do square root of 63. Here, let me just do that. I know that number is the square root of 63. So what's the square root of 63? 7.9 for y. So x-intercepts for this one, you're going to go 8 right and left of these of 1. So this will be at 9 and -7. The y-intercepts will be plus or minus square root of 63. So 7.9 and -7.9. I just know that from just some Pythagorean theorem talk. Number 60, your x-intercepts, none. You don't cross the x-axis. And your y-intercepts, because, yeah, it just doesn't reach. You got -2 and -4. Okay, now we're going to this problem. What I was going to state here is your x-intercepts might be able to be revealed based off this information. They might be -13 and +1, because even inside a square root function, it would be that. So my speculation here for x-intercepts are just -13 and 1. Anyway, y-intercepts, we'll see more when we talk about the graph itself. But factor form, I think, isn't really much for me here. So, okay, we're just going to move all these to the other side of the equation. We're going to keep it basic. Subtract x squared. Let's see. Should I put the 13 first? We've been kind of doing that before. 13 minus 12x minus x squared. It looks a little weird. It's anti-standard form, but it just kind of keeps the front thing positive. Plus or minus square root of 13 minus 12x minus x squared. Very weird looking equation. Now, if I were to predict stuff, I need to complete the square here. That would be x plus 6. So I'm guessing my center is going to be at -6, 0. And, wait, 0? Yeah, 0. And then add the 13 over 36 to 49. Radius is going to be 7. Radius is going to be 7. And that actually agrees with my x-intercept here this time, because that would make the 7 away from -6 is -13 and is 1. So that actually does agree with those that's going to be that. So I do believe this all works out. As far as y-intercept goes, 7. I'd probably have to look at the graph to know in my head exactly what it is I want to say about y. 6 away, 7. No, it would be the square root of 13. So I believe my y-intercepts, because otherwise I'm going to have to use the zeros on this thing, and I don't know how that thing works to do that. Oh, you can plug in 0 for x. I'm an idiot. Okay, so we can go to there. So let's go to the graphing calculator. Let's plug in this equation that we first have. We have square root. We have square root of 13 minus 12x minus x squared. Now I'm talking big game. These better be the equations. Oh, I skipped y1. I guess the square root of 13 minus 12x minus x squared. Yeah, I'm talking big game. I better be right. Otherwise, all this stuff goes moot. And then that one's negative. Will these fit? So these won't fit window range wise, right? So let's just shift everything over. Let's just go -13. Let's go -14.4. How much did I shift? 5 over? Let's go 4.4. And then we should be good as far as fitting it. So it keeps it within the square. Oh, I'm sorry. We have to zoom out. Okay, well, whatever. It's a circle, right? You guys agree? There's the circle. Now, for the y values, of the y-intercept is going to go up and down there. Now again, my center is going to be at negative 6, 0 right here. It hits x-intercepts at 1, 0, negative 13, 0. That's negative 13. And it's going up and down. Sorry, I'm not zooming it out. The y values, I believe, are at the plus or minus square root of 13. Now, if I want to see them, I can go to the table and plug in 0 for x. So let's plug in 0 for x. Let's look at both equations. And let's see this number here. If I substitute 0, I get these values for y. Now, is this the square root of 13? Let's find out. Square root of 13 around 3.6 something. Yep, 3.6055, which is 3.606. And there's that number there. So the y-intercepts, we're just going to use the decimal version, even though it is plus or minus square root of 13. Plus or minus 3.606 for those numbers there. Now the graph, let's get the graph back out. The graph was, although it's a little cut off, I'd have to change a lot of window ranges for that to make it right. So I did kind of the best I could. We can agree there, it's a circle still though, right? So. Okay, one more on that set, and then we got to see what's coming up at the very end of this problem, the last 6 problems after this. Number 62, we have x squared plus y squared minus 4x plus 6y equals negative 9. X squared plus y squared minus 4x plus 6y equals negative 9. Okay, this one, when it comes to solving for y, listen, whether or not we were trying to get into some circle form or whatever, completing the square for y would actually be relevant here. So I'm actually going to complete the square on both of them because you do have to complete the square for y in order to solve for y. That's just the nature of it. You are going to have to do that. So we're going to have to add the same thing on both sides here. We're adding 4 and 9 to complete the square there. This would factor into x minus 2 quantity squared. This factors into y plus 3 quantity squared. And this equals 4 on this side. Now I can solve for y based on subtracting this over and taking the square root, and the form looks a lot better. I could tell you straight off of this what the center is going to be at 2, negative 3. I could tell you the radius is going to be 2. As far as x and y intercept, you could do it based off this radius and center right here. The center, I'm going to predict these, 2, negative 3. X-intercepts, it won't have any x-intercepts. It can't reach. The y-intercept, because the radius is 2, it's just going to hit there at 0, negative 2. So no x-intercepts and a single y-intercept touching tangentially at 0, negative 2, like that. All right, no x-intercepts. So let's go ahead and finish the rest of this equation, by the way. We still have to actually solve for y. We have y plus 3 squared equals 4 minus, and then x minus 2 quantity squared. We take the square root of both sides. We get y plus 3 equals plus or minus 4 minus x minus 2 quantity squared. And then we subtract 3 over, so we get y equals negative 3 plus or minus the square root of 4 minus x minus 2 quantity squared. So maybe that is what they wanted you to do. It's like, take the knowledge that you have of graphing circles to kind of come up with the information to make sense of it, specifically on completing the square. There's no other way we're solving without that. So we're going to get to that. We have negative 3 plus the square root of 4 minus x minus 2 quantity squared, like that. And then we also have the other one, which is negative 3 minus. It's still a negative 3, but this part's the minus, square root of 4 minus the quantity x minus 2, and that is also squared. Now I got to change my window range kind of back. It should fit in this, I believe. There shouldn't be a problem. 9.4. Okay, so here should be a graph kind of right here. There it is. The center is at 2, negative 3, and it's hitting the y-intercepts just at negative 2 tangentially. It's not hitting anything else. So there's the last graph there with that information present. Okay, and that's the last one there. So we have 6 more problems to go. Number 63, the period of a pendulum is the time the pendulum takes to complete one back and forth swing. So how long it takes from here to back, and then you're done. The period t in seconds can be modeled by the function t equals 1.11 times the square root of L, where L is the length in feet of the pendulum. So if it's longer, it's a bigger pendulum, it's going to take longer to go. Graph the function, estimate the length of a pendulum with a period of 2 seconds, explain your reasoning. Now, I don't know if they mean use a graphing calculator or not. They probably don't when they say graph this. So let's use one of the bigger number types right here. Maybe they do. I don't know. But 1.11, that's something kind of interesting to talk about here. So got to point at the origin here. It's a vertical stretch by a factor of 1.11. So over 1, up 1.11. Over 4, up 2.22. Over 3, or over 9, up 3.33. I sound smart by saying that. I don't know why. All right, they said, now here's the thing. They said estimate, there's the graph. I'm using my hand-drawn one. It's a pretty good thing. Estimate the length of a pendulum with a period of 2 seconds. So the period is t. Remember, this is t and this is L. So here's a period of 2 seconds. They said estimate the length. I'm going to estimate the length to be close to about, I don't know, let's say 2.7 feet, 2.8, I'll say 2.8 feet. Did they say feet? L is the length in feet. Now, I don't know if that's it exactly or not. I don't know if they actually wanted a graphing calculator for that. So what we could do instead, let's go to the graphing calculator and type the same thing and just see exactly how close I was. I might have been off by quite a bit because I just did it based off a curve or based off a hand-drawn thing. So 1.11 times the square root of x gives us this graph. I mean, my graph was right-ish, but what we want to do is look in the table. Let's go by increments of 0.1 starting from about 2, and let's figure out where we're getting a y value of 2 at about. Oh, man. Oh, I was off with my curve then. So it looks like it's closer to about 3.2. I'm going to shrink it to one more decimal place here, so 3.2, and go by increments of 0.01, like this. Now listen, we could solve this. We could solve it, but they said use an estimation. So 3.24, 3.25. So I'm going to say it's actually about 3.25. 3.25 feet. They said estimate. They didn't say use the graph to estimate, so now I kind of feel bad. Maybe we weren't supposed to do that. So let's do the actual calculation version of this, how we're going to get around 3.25. We're going to substitute 2 for t. We're going to get 2 equals 1.11 times the square root of L. I wish I read the question a little bit more. I'm going to divide both sides by 1.11. Even though it started off as a radical, now it's square root of L equals 2 over 1.11, which is clearly not a easy number to write. So we've got to square both sides. Square both sides here. And we're going to get L equals 2 over 1.11 squared. So this is the one we want to calculate. This is where you're going to get a number really close to 3.25. So going back to the calculator, let's do 2 over 1.11 squared. And this number is your 3.246. So that's your around 3.25. And that's the feet of the answer. So there were a couple things I might have done wrong here. First of all, use my graph to estimate it. Second of all, using a graph to estimate it. Here's the solving version. So I don't know. I covered all my bases. I did graph it by hand. Whether or not they wanted me to even do that is uncertain. Number 64, how do you see it? Does the graph represent a square root function or a cube root function? Explain, and what are the domain and range of the function? Well, a cube root function would have an all real number domain and range, and it would kind of squiggle both directions. Square root function does not. So on number 64, that is indeed a square root function. Square root function, if for any other reason, because the domain and range are limited. Cube root functions don't limit domain and range. They don't rim it. So the domain of this one, the x's go to the right of, your vertex is negative 3, 1, right? So x is greater than or equal to negative 3, and your range is y is greater than or equal to 1. That's the bottoming out portion of that. I like how do you see it. They tend to be shorter. Sometimes they don't even ask you to explain. Number 65 on problem solving. For a drag race car with a total weight of 3,500 pounds, the speed s in miles per hour at the end of a race can be modeled by that information. I mean, everyone knows this, right? 14.8 times the cube root of p. Where p is the power in horsepower, graph the function. All right, I am going to use the graphing calculator this time. Now, this does have a vertical stretch factor of 14.8. So what I'm going to have to do on this one likely, I mean, I don't need the graphing calculator per se, but I want to get as many points as possible. And I want to change my window range this time. So it's going to be like over 1 up 14.8 and over 8 up 29.6. So we're probably going to go up to like 30 and negative 30 on this thing here. So we could probably even use the tall graph and use it in the tall way. 14.8. Oh, and here's the other thing. I don't think you have negative horsepower. So it says graph this thing, but I don't know how much it matters to do the negative end. So I don't know. X. Okay, here's the thing. If we graph it right now, it's just going to be super tall. In fact, it was so tall. Look at that. You can't even see it. So we really do have to change our window range. Remember how I said we would have to go over 8? Let's just go to 10. We could go... Okay, these are fine on X. For Y, we're going to have to go up like 30 and down 30. Because we'd have to go over 8 to go up 29.6 or whatever. So this will be fine. Let's go negative 10 and 10. This will be fine for us to be able to see the curve like this a little more. But when we graph this, we have to appeal to that kind of scale like that as well. So there's that curve. Let's go ahead and sketch it. I'm going to use the tall graph this time. It's a little bit unconventional to do that for cube root functions because normally they go out so much more. But I'm going to go by 2's on Y. This will be 10, 20, and 30. X's are fine to be normal. Okay, so this is 5 and negative 5. Okay, when I go over 1, I'm going up 14.8, which is pretty much 15 like that. And same with left 1 and down 14.8. Now, once again, I don't believe that this negative domain, the negative speed or negative horsepower or whatever should really apply, but they just said graph the function. They didn't talk about domain at all yet. And you go over 8 to go up 2 times 14.8. So that's 29.6, so really close to 30. So might as well look like 30 right there. And then negative 8 and down to about negative 30 like that. So curve is looking curvy. Let's go. I'm trying to be as precise as possible here. Let's go like that and like that. It's a cool curve. I like it. Okay, that's actually kind of cool. All right, so they said graph it. That's not even part A. Part A, determine the power of a 3,500 pound car that reaches the speed of 200 miles per hour. Now this is clearly not using the graph for it. This is clearly using substitution. S is miles per hour. And yeah, we only get up, our graph only shows up to 30 miles per hour. So we're just going to do a substitution here. So 200 equals 14.8 times the cube root of p. Maybe we were supposed to do this for the first one. Cube root of p equals 200 over 14.8. I'm just going to leave it like that. We got to cube this. Cube both sides. And we're going to get p equals 200 over 14.8 cubed. All right. So this, I'm going to use the calculator. 200 over 14.8 and cubed will be 2467.77. So around 2468 horsepower. Okay. Part B. What is the average rate of change in speed as the horsepower changes, or as the power changes from 1,000 horsepower to 1,500 horsepower? Okay, so what we need to do is take S of 1,500 minus S of 1,000 over 1,500 minus 1,000. Okay, we're trying to see the average rate of change in speed. So it's a slope from this y value minus this y value over that minus that. So we have the graphing calculator. We can go to our table and we can ask for the numbers. Let's just go to ask. We can ask for the numbers 1,500 and 1,000, and we're going to subtract these two numbers out. Now, this is not an exact number, but I'll make do if that's okay. So we're going to do around 169.42. Since we're going to round anyway, it's probably fine. So 169.42 minus, it looks like an exact 148 all over 1500 minus 100, which is 500. So we do 169.42 divided or minus 148 divided by 500, and that's about, it's a weird number, but 0.0424. So the average change in speed, the average rate of change in speed is we're changing an average of this many miles per hour per 1 horsepower. I think horsepower is normally lowercase HP. I don't actually do a lot in things in driving, but that's what I believe it's going to be. So remember, we're doing a slope, we're doing a rate of change when we're talking about those bits. And in order for that thing to work out the way that it does, we're actually working out horsepower in that way. I don't know. Anyway, so that is, what question was this? This is number 65. So that was number 65. Okay. Here we go. Number 66, thought-provoking. I think that means open-ended. The graph of a radical function f passes through the points 3, 1, and 4, 0. Write two different functions that could represent f of x plus 2 plus 1. Explain. Okay. So we need to pass through 3, 1, 3, 1, and 4, 0. Okay? One graph I'm thinking about could have this as the vertex, which means we go up and to the left, like that, which means we translate 4 to the right. So let's call this one f of x. So this would be f of x. I guess they're both f of x's. So one version in green, though, would be the x inside is negative, but it would be the square root of negative, and this would be x minus 4, like that. If you recall from some of the previous questions, we need to have the negative factored on the outside like that. You could distribute it, so that would be square root of negative x plus 4, like that, but it's still 4 to the right, and that still does that. So that's one version. The other version, that was probably the harder one. The other version is to go down and through that way, but this time this is the vertex right here. So this f of x equals, this vertex is at 3, 1, and it's going downward. So flip this over. 3, 1, like that. So these are the two equations. So it says write two different functions that could represent this part now. Now we got to do f of x plus 2 plus 1, like that. So I think from these two, we have to now do f of x plus 2 plus 1, if that makes sense. Let me use green still for that one. So for this one, we're going to do f of x plus 2 plus 1 equals, and we're going to plug in x plus 2 in for that x. And then we'll have a plus 1 on the outside of the function. So that'll equal, I mean, if you truly do distribution again, negative x minus 2 plus 4 plus 1, which is negative x plus 2 and plus 1. Basically, it takes this graph and it does what? It translates it 2 units left and 1 unit up. So this is the new appearance of the graph. Wait, is that right? X plus 2 plus 1. Translates 2 units left and 1 unit up from there. Oh, it's this graph. It translated 2 units left and 1 unit up from there, like that. Anyway, so there's that one. Now the other one in blue, I probably should have written these down below to begin with. Negative x minus 3 plus 1. All right, so this one, f of x plus 2 plus 1 equals negative, and inside we substitute an x plus 2. We're going to subtract 3 there, and there's a plus 1 on the outside, and then there's another plus 1 there. This plus 1 is part of the original function. This plus 1 is added to the function on that. Here's one answer, by the way. The other answer would then be 2 minus 3 is negative 1, so minus 1 there, and 1 plus 1 is 2. So this graph should have a vertex at 1, 2, and should go upside down. So 1, 2 like that, that's the over 2, 1 up. So I believe those are the two things that they're looking for, is trying to find out what the two functions would be specifically, and then shift them two left and one up and what they become. Right? That's the substitution of it. Okay. Number 67. Two more questions. Number 67. Of course, this has two parts. The terminal velocity v sub t in feet per second of a skydiver who weighs 140 pounds is given by v sub t equals 33.7 times the square root of 140 over a. I'll tell you what, for my cheesesteak stuff today, it probably weighed that much. I'm close to it, just kidding. Where a is the cross-sectional surface area, all right, well, it's this part of the table, in square feet of the skydiver. I don't know much of what that means. That's okay. The table shows the terminal velocities in feet per second for various surface areas in square feet of a skydiver who weighs 165 pounds. As long as I just substitute some things and don't interpret it, I'll be fine. Which skydiver has a greater terminal velocity for each value of A given in the table? So, timeout. Are they already computing these for me? Do I not have to plug in? So I don't have to plug in these values into here because they're already computed. I believe they're saying it. So which skydiver has a greater terminal velocity for each value of A? Or do I divide those things by A again? I'm trying to now make sense of this here. Which skydiver? Oh my gosh, I'm confused. Oh, this weighs 100. Hold on a second. Hold on. I didn't read this. This is a function for the 140-pound skydiver. This is the function for the 160. These are the table values for 165 pounds. So okay, that makes more sense. This is 140 pounds, and then the other one's 165. So what we have to do is substitute these values for A in the 140-pound one and compare them to those values here. So here's what I'm going to do. I'm going to copy paste that table over. Note that that one's for the 165-pound person, probably how much I weigh now after the cheesesteaks. And then write that next to it in the table. Now I understand. Okay, so this is 165 pounds, and let's get the 140-pound values. 140 lbs. Okay. So let's go to the calculator. I thought they gave us the numbers. All right, I'm going to substitute 33.7 times the square root of 140 over x, that's our A, and let's plug those values in. Not these numbers, that's too much terminal velocity. Let's substitute 1357. Okay. So for these, I'm going to write these numbers in. So I need 398.74, 230.21, 178.32, and 150.71. Okay, so I got these numbers here. Hopefully you understand this is V sub t for the 140-pound folk there. So we're comparing each cross-sectional surface area. So I'm just going to kind of write inequalities for these. For cross-sectional area, surface area of 165 pounds wins. For this one, they win, and they win, and they win. So it's greater for all four of them for 165 pounds. So for part A, which skydiver has a greater terminal velocity? 165 pound individual. Part B, describe how the different values of A given in the table relate to the possible positions of the falling skydiver. Well, I don't know how cross-sectional surface areas work outside of the fact that, well, they said terminal velocity. They didn't say increase your velocities, you increase. The idea is, guys, you increase in speed as you fall down more. But terminal velocity is you cap out at a certain speed over time. But the higher up you are in the air, like that Felix Baumgartner, the one who did a skydive thing from space, basically, he reached a higher terminal velocity because he was Not because he was higher up, because he had thinner altitude. So my guess is, and I don't know what cross-sectional surface area specifically means, my guess is higher terminal velocity means higher altitude. Is my guess. I don't know. So when it says describe how the different values of A relate to the possible positions, I think it means that you're higher up in that way. It could also, of course, if you think about it, mean that you're maybe not falling so much vertically. It says cross-sectional, so maybe it's about this. Maybe you're falling more horizontally. I mean, the Earth curvature and how you jump out and things like that can also possibly change. So I don't know if they're going to apply things to the altitude. I think they're probably going to talk about vertical versus horizontal. So a higher cross-sectional surface area, I think, means you're more vertical, right? Because velocity just is velocity. But a higher cross-sectional surface area, this is my guess, surface area means more vertical fall. Whereas a lower, no, a lower cross-sectional surface area. Whereas a higher one means more horizontal fall. Now that I heard cross-sectional. All right, anyway. I don't know. That's just interpretation. And finally, number 68, mathematical connections. We got a cone, people. The surface area S of a right circular cone with a slant height of 1 unit is given by S equals pi r plus pi r squared with a slant height of 1. Oh, yeah, that's true, because the pi r L, pi r times 1 plus pi r squared, where r is the radius of the cone. All right, use completing the square to show that that is true. Okay, we're gonna have some work on our hands. So I'm just gonna start completing the square and go from there. Keep in mind, what we actually have here is this is the quadratic term. So this is pi times r squared plus pi times r. Now, if you want to complete the square, you're going to have to add something right here. And keep in mind, pi is your constant of both of these things. In order to do that first, actually, before I do that, I need to factor pi out. I need a 1r squared there. So factor pi out, you'll have r squared plus 1r, which I actually kind of prefer that right now. Now, whatever I add here, I also have to subtract outside here and multiply by pi. Okay. Now, from there, we divide, this is a 1. We divide 1 by 2, and we get 1/2. We square 1/2, and we get 1/4. So this is pi times 1/4 that gets subtracted out here. So this is S equals pi times, and this factors into r plus 1/2 quantity squared, and this is minus pi over 4. Now, I need to start solving for r, so a couple things are going to happen here. First of all, pi's already factored out, so I can't factor it out twice. I can add pi over 4 to this side, so I get s plus pi over 4 equals pi times r plus 1/2 quantity squared. I can divide both sides by pi. Now, when I divide by pi here, s gets divided by pi, and this pi over pi cancels out, and you have 1/4. Although when I look at the final result, I'm trying to decide if I need to divide by pi outright or if I should be just taking the square root. Let me think about that. Give me 1 second. I divide by pi here. That's gone. That's a 1/4. Now, maybe I don't divide by pi outright right here. I think what they want to do right here is multiply the whole thing by 1 over pi. See, the thing is, what I wrote was fine, but I need to match their answer. So they have 1 over pi on the outside. So let me write r plus 1/2 squared on this side right now. This is r plus 1/2 squared equals 1 over pi times the quantity s plus pi over 4. It's like that, okay? Now we're going to take the square root of both sides right here. And now we'll have r plus 1/2 equals. Now here's the thing. The square root of this can be split up in several ways. There's a product and a fraction. This is, first of all, it's a plus or minus, but because r can only be positive, it will be a plus. Square root of 1 over square root of pi times square root of s plus pi over 4. Now, my last thing to do is subtract 1/2 from both sides, but also the square root of 1 is just 1. So I can write this as 1 over square root of pi times the square root of s plus pi over 4, and all this is minus 1/2. And that matches what they have there. So Again, I needed to write it in the way that matches what they have as opposed to something else, and that should be part A. Part B, graph the equation. I doubt we're supposed to do that by hand. Graph the equation part A using a graphing calculator, then find the radius of a right circular cone with a slant height of 1 and a surface area of 3 pi over 4 square units. Okay, so we'll go to the graphing calculator for the last part on B. We are going to type in 1 over square root of pi times the square root of, S is our x this case, x minus pi over 4, close that, square root, minus 1/2. All right, let's go to the graph. Whoa. All right, let's change our window range. Oh, this is something where I don't know what kind of window range we need. I have no idea. That looks like it did a lot of things at once. I'm going to start with this one and see if we can see anything on this graph. It says graph the equation. Excuse me. Oh, it's something really tiny. Okay, so we have this here. We need to end up finding with a slant height of 1, which is already there, and a surface area of 3 pi over 4. Now, 3 pi over 4 is close to about 2 point something, so we can probably figure it's somewhere within there. So I can even trace it. I can do the trace feature on the graph or find value. So let's just put 3 pi over 4 here and see what it's actually hitting at for a y value instead of going to the table. So it's that one right there. Let's zoom in on that. I hope I can go zoom right in on that specific point. I think it's near it. So let me see that one more time. This is the part. By the way, here's the domain restriction, right? It's a square root kind of function. So they're talking about this. It's around 2.4, it looked like. Let's do it one more time. 3 pi over 4 is our value. So it's this. When x is 3 pi over 4, y is 0.207. So I'm going to say r of 3 pi over 4. Excuse me, not r. r of 3 pi over 4. Your surface area of 3 pi over 4 is about 0.207. And radius is in, it's just units. So just 0.207 units. And I guess that would be the radius for that one. And we're using our function for it in order to get her done. So unless I type something wrong in the actual graphing calculator itself, right, that's what we're looking for there. I want to make sure that I typed it all correctly though, because otherwise, otherwise things will go awry. So let's go and take a look that I did that. Because I had a, did I type a minus? I might have, hold on a second. Ooh, I typed a minus in here. Hold on, this is supposed to be a plus. Hold on. Everything changes. Guys, everything changes. Even the graph. Now the graph, it's a little bit taller. Still in the same spot. So let's do that one more time. It's not 0.207. So let's go one more time. Value, 3 pi over 4. I even have a plus in the equation. I just wrote it wrong. Oh, 0.5. So it's exact. So let's do that again. It's not approximately this. It's exactly 0.5. Sorry about that. Now, could have I done that with the stuff here? Probably. See, check this out. Let's try that here. Let's do 1 over square root of pi times the square root of, here's 3 pi over 4 plus pi over 4 minus 1/2. 3 pi over 4 plus pi over 4 is 4 pi over 4, which is pi, right? So that's 1 over square root of pi times square root of pi minus 1/2. Pi's cancel out. You have 1 minus 1/2, which is 0.5. Okay, so that cleans up anyway. So 0.5 units is our final answer. All right, guys, that'll do it for this one. This is Mr. Robinson. Thank you so much for watching. Take care. I will see you in the next one.